hypoxia ischemia animal get, but we didn't clamp the carotid artery, we didn't decrease the oxygen that they were receiving. We didn't create the injury. And if you look at here, in green is the cytochrome C oxidase, that's metabolism. This is oxygen saturation, this is flow. And the axis of flow, metabolism is here. This is just oxygen saturation and blood flow, and absolute values here, absolute units. And you can see, if you don't have hypoxia ischemia, everything stays flat, okay? That's control. This first example here, you see, when the yellow portion here is when we induce ischemia, is when we clamp the carotid artery, okay? And after that, during this as a shaded region, we drop the oxygen that the animal was breathing to 8%, growing from 20 to 8%, to create this condition of hypoxia ischemia. Because this baby, not only their carotid arteries the umbilical cord is clamped, but also oxygen that they receive goes down. So that's how you create this condition. And you can see, if once you do the first part, you see flow goes down, metabolism is delayed. You see green curve is delayed in all of them. The green curve is delayed. And that's because we have this physiological reserve. The body has a little bit of a reserve. Even the brain has a little bit of a reserve that it can live on, but for a very, very short period of time. So when the flow goes down, you see metabolism goes a little bit down, but it's delayed, and now it starts crashing. And once, at this point, we release the clamp and also bring in back oxygen, and you see everything goes back to normal, okay? Except for oxygen saturation, the cerebral oxygen saturation overshoot, and this is characteristics. And we have the same thing for all three animals. I'm just showing here 3 examples, but it was a larger study. So what I wanted to illustrate here, yes? Yes? Yes, that's a great question. And please feel free to raise your hand and ask questions throughout. So what happened here is that when you have hypoxia ischemia, so this already happened. You are monitoring here because the baby the delivery is happening when all these drastic changes are happening. You cannot catch them. So what we were showing here is to demonstrate that we can monitor all these different parameters. Okay? Because we know that in this condition, they're going to change drastically. Unfortunately, you will be at this point here when the baby is out and you can start monitoring it. And you see, it looks very stable there. But my next slide, I'm going to show you. Now, this is how you monitor. So in this case, hypoxia ischemia happened here. But if you monitor here, we were monitoring here the oxygen metabolism, oxygen consumption. And you see, this is control. And you see, there is a gap. So for the hypoxia ischemia, you have metabolism is depressed. And the reason why metabolism is depressed is because probably you have an injury. When you have injury, those neurons are now injured. They are not consuming oxygen anymore. Then you have a drop in metabolism. This is what you use. You use this difference. You know that metabolism should be high here. If any of your patient has a metabolism that is in this range, then you know they are injury, and you have to intervene. And on top of that, you can use metabolism to distinguish between mild, moderate, between mild and severe. And that's very important, very, very important, because the treatment decision depends on what kind of injury. It's a severe injury, the likelihood is that probably, so in this example here I have here, red is the severe, this is the moderate, and this is the control. And you can clearly distinguish these 3 groups, okay? And so I want to mention that I was not involved in this study, okay? This is a study that was done in the same institution where I am, and was done using piglets. But this, I'm just wanted to illustrate that, to show that, yes, you can distinguish, you can use metabolism to distinguish between the severity of hypoxia ischemia. So now I'm going to move to clinical application, because that's basically what matters, okay? So you develop these technologies, you validate them, you test them in animal models, but how does it work in humans? So this is NEMO. I didn't coin the name. My previous PhD student, AJ, coined the name, neonatal neuromonitoring. So I let the student, when they develop a new device, I let them coin the name. And they come up with interesting name, NEMO. NEMO like the fish, but a little bit different. So this is a device. It's open here, and you can see here you have sound dampening material, because this device is used in the neonatal intensive care unit. It's a very quiet environment, very, very quiet. You don't want to hear anything. And in this device, we have a multiplexer that is based on shutters, so mechanical shutters. So we make a little bit of a clicking noise. So we dampen the noise, and we slap the logo of our research institute on the side, and these are the probes. So you have 3 optical fibers that come from here. They are here. They come out here from the front, from this opening. They come out, and this band goes up around the head of the subject, and we place the probes here. The probes, you see these grooves here? The probes just slide into those grooves and stay there. They don't move. And this is an example of the probes on the head of a baby in the crib, okay? So, and during the monitoring. And in this next few examples, what I'm going to showing is how you can continuously monitor the absolute cerebral blood flow at the bedside. So, preterm infants are known to be at high risk of brain injury. And one of the main brain injuries is ischemic brain injury with ischemic encephalopathy. So the primary results, this is due mainly to, they have low blood flow and their hemodynamic, they have unstable hemodynamic, and on top of that, their autoregulation is not well yet developed. So if you have fluctuation in flow, it can lead to ischemia, and that's really serious. So that's why it's important to monitor these babies. So this example here, what I'm showing here is the change in flow measured by the dynamic contrast enhanced technique that I was mentioning. It's just another validation of the fact that DCS, diffuse correlation spectroscopy, can measure flow. In the previous example I will show, it was in animal. Here, it's in human, babies, preterm babies. And in this infant, we monitor the flow. So in this example, what I'm showing here is we are monitoring flow over time. So the baseline here is, there is no change, right? It's 1, because you understand that, right? I mean, here it's 1, because the flow was not changing, okay? That's my baseline. And over time, we see a drop in flow. And why? Because in this case here, this was a study on infant that has patent ductus arteriosus. So patent ductus arteriosus is a heart condition. So babies who are born, and one of the valves is not closed, it's open, it's patent. And the previous way of treating this condition is that you do an endomethacin infusion. Endomethacin is a vasoconstrictor. So when you infuse endomethacin, so all the vasculature around the body, they constrict, including in the brain and also in the heart. And when the vasculature there constrict, then the valve closes, and then from there the duct is now closed. Okay, and we tag onto this study because that's the clinical treatment that they used. I think they stop it now, but that was the clinical standard. We tag onto this study to monitor, and we can see here blue is baseline before endomethacin infusion, And when they start infusing indomethacin, you see flow goes down. And so this is change in flow measured by DCS, okay? You only measure change in flow. So this is, baseline is whatever the flow was, we don't know. And here, it drops to about, now you have a drop to about 30% drop in flow. Well, how do you know what was the flow? And that's where now the ICG, the tracer kinetic modeling, tracer kinetic technique comes in. If you measure flow anywhere here, blood flow, at the beginning or the end or anywhere here, you can now take that absolute flow and scale this relative change. And that's what we did. You see, pay attention. Now this is relative change, boom. Now I can see, I take the absolute flow that we measure at the beginning or at the end, because we measure flow at the beginning and at the end. And then you scale now. You see units, the units are now in millimeter of blood per 100 gram of tissue per minute. And here, the baseline blood flow was around 14 units of blood flow. And when we dropped to around 9. That was a significant change in flow, okay? So this is a technique that allows you to monitor absolute blood flow at the bedside. And this is the only technique that exists in the world. This is the only technique that exists that allows you to monitor absolute cerebral blood flow at the bedside, okay? Now, we apply this also to ventricular. So this condition here is ventricular omegaly, and this is typically happen when in more tropical countries, this can be caused by infection, okay? But in our country, like in Canada, in developed countries, mostly this is caused by periventricular hemorrhage. So these are babies who are born and they typically preterm, and they have a hemorrhage around the ventricular area. And if you have this hemorrhage, so the blood will get into the cerebrospinal fluid, and the cerebrospinal fluid become thick and will not drain. And then you have this ventricular omegaly. So this is a baby here that has this condition, hydrocephalus. It's called hydrocephalus, which is accumulation of water, of liquid, which is CSF, in the brain. And the condition to treat this is that to come in, and you come into the frontal with a needle, you puncture the needle, the frontal, and get into the ventricle, and then let the cerebral spinal fluid drain. And you repeat that every few days until the situation resolves. So this is my colleague Sandrine de Ribaud-Pierre, who's a neurosurgeon, who's draining the ventricle from this baby. And once it's done, so she just stopped. It's called ventricular tap. Some of these babies will have multiple ventricular tap during their stay in the intensive care unit. And we monitor this baby during the procedure. So what we saw here is this is a change in flow here. We didn't see much change. So the ventricular tap start here. The gray area here is where the ventricular tap, this is before the ventricular tap. This ventricular tap starts here at 2 and ends here. And this is the post-ventricular tap. And when we monitored, we didn't see much change in oxygen saturation. And all the commercial near-infrared spectroscopy, commercial NIRS device that you will buy from a supplier, it will monitor this parameter here. We didn't see much change. Flow didn't change much, start to creep up here. But the important point here is the metabolism. We realized that once they were doing this ventricular tap, metabolism goes up. And this is telling us that they were likely a metabolic stress. So this, because when this baby has hydrocephalus, you have the ventricles, you have an accumulation of fluid in the ventricles, and what it does, it pushes the brain against the head. And because of that, so probably the brain was squished, and that's why metabolism went down. And once we did this, after the relief, you see metabolism goes up. Because metabolism typically doesn't change this much. So this infant was likely going through a metabolic crisis. And we compare them. So this is just this was an example. This is at the population level. When we look at all the subject in our study. And they confirm what what I just mentioned there. And we apply this also, we apply the technique to adult going under cardiac surgery. So this CPB here stands for cardiopulmonary bypass. So when somebody is going under heart surgery, typically what happens is they stop the heart, obviously, in order to operate on the heart. And there is this machine called the heart-lung machine that take over the function of the lung and the heart. So this machine will circulate the blood, okay? So they will have two lines. One goes into the artery, one goes into the vein. So they will drain from the vein and going back into the arteries. And this machine, then the blood goes into this machine. And this machine's job is to pressurize the blood so the blood can circulate into the body. And also to oxygenate the body, oxygenate the blood. And you can imagine this is create a lot of hemodynamic stress into the body. And we monitor this. When the people are going on cardiopulmonary bypass, and when they come off the cardiopulmonary bypass, and you see there was a decrease in metabolism. Oxygen saturation, we didn't see much. Okay? And I say again, oxygen saturation is what you can measure with typical blood. You can measure with typical NIRS device. But here, we were able to see this change in cytochrome C oxidase because cytochrome C oxidase is mostly in the brain, doesn't have on the superficial layer. And in adult, it's a kind of a challenge, actually, in adult, to monitor the brain with adult. And because of that, I'm going to now, this is the end of the application. I'm going to go back to now technological development and a little bit of a theory. That's my last few slides. And the reason why we're doing this is a new project in my lab, new about 2-3 years ago now. And the motivation is that when you want to monitor the adult brain, it's very difficult. And the reason probably we didn't see anything with this oxygen saturation here, cerebral oxygen saturation, is because in the adult head, in neonate, you have a very thin, about 3 millimeter. The scalp, which is the skin, and the skull is very thin, about 3 millimeter. For an adult like me, it's going to be 10 to 15 millimeters. So the light has to go through all this tissue before reaching the brain. And because of that, only about 15% of the light get into the brain. Most 85% will be just scattered through the extracerebral layers. And how do you tackle this problem? Use time resolve. Simple. With time resolve, you send a pulse of light and you wait. Okay? So if you look at the photons that arrive late, the late arriving photon, those late arriving photons, they have probed the brain. That's how you improve your sensitivity to the brain. And people have been using this for quite a while, but they are limited to a few wavelengths, just 2-3 wavelengths, and that's what we also have been using. But that's a limitation. With that, you cannot monitor cytochrome C, because cytochrome C, to monitor cytochrome C, you need multiple wavelengths. There have been work that suggests that you can use 18 wavelengths, but from our experience, you need dozens of wavelengths. And how do you do that? Using time resolve. That's very difficult. Alicia's colleagues at Politecnico di Milano, so they have a device where they scan the wavelength one by one. It allows you to monitor, to have all the wavelengths, but that's too slow. You cannot apply that clinically. It's too slow. Okay? And the other technique is to use now a large straight camera and acquire all the data simultaneously. That's very expensive, and the stick camera, they don't have the right characteristic for what we want. If you want to focus on the late photon, they're not good for that. What do you do? Well, you go back to engineering. This is what we did. So this is a supercontinuum laser. So this supercontinuum laser emits pulse of photons. This is a time-resolved laser, but it's a white laser. It emits multiple wavelengths, so it's continuous wavelength. It's like a halogen lamp, but pulse, okay? If I can model that. So, and this is where the engineering comes in. So when the light comes in, it goes to the tissue mimicking phantom, or human, it can be a human. And then when the light comes out of here, you have all these pulses. So you have pulses of wavelength from, let's say, 650 to 850 nanometers. And you channel them through an optical fiber. You come here to an optical grating. And the role of this optical grating is to disperse the light into its wavelength component. And once you do that, so instead of now having, typically after that, you have a camera. We take this is called a digital micromirror device, and we have a single pixel detector. And we apply the principle of compressed sensing. What we do here is, this device here, the digital micromirror device, we can show a pattern, okay? Once we show a pattern, we show a pattern here. Here I'm showing Hadamard pattern, but you can use as a pattern. It's this H of P, this Hadamard pattern. The intensity here, that is here, that goes from the diffraction grating, because you see, the diffraction grating spread the light, okay? So it's this I of X and Y and T. So on the Y-axis, it's the same wavelength is on the Y-axis. T is just because it's a temporal component. It's a time. It's a pulse. It's a pulse. You know, now what you're doing here is you're projecting your intensity onto your Hadamard pattern, and if you do that, you can measure this A of T. It's just a time-resolved curve, just a single pulse curve. You measure this, all this. You measure. Now you change your Hadamard pattern. Okay, you go through your base of Hadamard pattern, then you acquire a bunch of A of T, and then you do your reconstruction, where you take your AFP, you multiply by your Hadamard pattern, you do your minimization, you have your intensity. So basically, by using this, what we have demonstrated that you can, let's see if I can, you can get this three-dimensional, this is time in picosecond, and this is wavelength. Alisa, you have a question?
Yes. Just a quick question. I think it would be interesting to know, for example, how many octaves do you use, and how fast it is.
Exactly. So that's a great question. So if you want to go slowly, your number of patterns is going to be the number of wavelengths. But that's very slow. But because if you look at those curves we had, we know that those curves, if you look at the extension coefficient of oxy, deoxy, water, cytochrome, those light absorbers, so they are sparse in the spectral domain, and we take advantage of that. So typically here we show about, I can't remember on top of my head, like about 10 to 20 patterns was enough, and we were able to get to 20 seconds. We were able to acquire all of this in 20 seconds. Now we are moving forward to making our device faster. So we want to go to sub-millisecond. So we're going to want to go to sub-millisecond. And we characterize it compare it to a regular spectrometer. So our resolution is similar to a resolution of a typical diffuse optical spectroscopy spectrometer. And these are the individual, if you took any wavelength here, so you have a bunch of them here. So here we have 201 wavelengths. So we have a range of 650 to 850. And the nice thing, we're flexible. We can move our spectral window whenever we want. Okay? And we just published this paper. If you are interested, go to this paper. It provides this paper and the previous paper. They provide all the details you need about this technique and its characterization. I'm just going to stop here. So this is just part of my group. Some of them are here, some of them are here, but so, yes?
Sorry, I have another question. For the reconstruction,
Mm-hmm.
because you have to do the reconstruction, how does that work?
Yeah, so,
I mean, is it...
so these are your measurements.
Yeah, how fast is the reconstruction? I mean, is it something you can then, the results are something you can obtain in real time, or you have to...
So in this case, we didn't obtain the result in real time, but our goal is to go to real time right now. So we're going to move to real time. So what's going to happen is we're going to be projecting these Hadamard patterns
Yes.
Okay, we already have the software that controls this Hadamard pattern. So the Hadamard pattern will acquired. We project the Hadamard pattern. We measure the AFT, do the reconstruction. Once we finish all the Hadamard pattern, it's going to be like in 1 second, and do the reconstruction right away. So either it's going to work on software or we're going to implement it on hardware.
Okay, okay. Thank you very much.
Maybe another question?
Thank you for the presentation. My question is regarding the disease varicose vein. And
sorry, the disease?
Varicose vein, where the walls of the veins are damaged or the valve is not working properly, and therefore blood flows backward. Can you use this DCS to diagnose those kind of diseases?
No, you cannot use it to diagnose the disease, but you can use DCS to see the effect of the condition on the brain. So typically what would happen is they will come and do, let's say that there is an intervention. So these techniques are very useful for that, to monitor the effectiveness of an intervention. You have a clinical intervention, and this clinical intervention should do less to the patient. So you monitor the brain for sensory. But it will not be able to diagnose it. That condition is better diagnosed using ultrasound.
Thank you. Any other question? Online, is there any question? So let us thank the speaker. Our next speaker is Dr. Mpato from ICTP. He will talk on digital orography, microscopy.
Good morning. Okay, today I decided to, Chief, I will start with photothermal spectroscopy. I hope I can cover the whole topic. And then in the next presentation tomorrow, I will go to digital holography, because for me this is more important now, and for you also. Let me try. Okay. Okay, I will try to cover this topic, the fundamental of photothermal spectroscopy. I will demonstrate why it's a very high sensitive method in comparison to, let's say, spectrophotometry. I will cover the theoretical background. Then I will demonstrate experimentally this theoretical model. And I will go to the application. One of the applications will be miniaturized gel electrophoresis with photothermal detection. And at the final of the talk, I will cover a little about photothermal interferometry. Instead of the detector, I will use camera for an interferometry. And this will be like a bridge between photothermal and interferometry to more, because they are related. Okay? And finally, the conclusion. Let's first understand a little, let's say, one example. In diet, when you excite a sample, what happens? Where this energy is going? When you excite a sample with any wavelength, matching the absorption of this sample, let's say a dye, you have the ground vibrational level, the is 1 and is 2. For example, you excite here, you have an internal conversion, and this energy, where is going this energy? This energy is going through the thermal relaxation. You have interaction between the molecules and the temperature of the medium increase. However, we can have also here internal conversion also that give also thermal relaxation. We can have emission, we can have also fluorescing and intersystem crossing. This energy and this process have different relaxation time. It's important to understand this because we will follow this process after, and you will understand why photothermal is a high sensitive method. You can see there 10 to minus 9, let's say nanosecond, or 10 to minus 11. Now, okay, regarding the medium, if we have, for example, a cell, a cuvette, with some liquid inside, water, whatever it is, you excite this sample with the pump laser. Part of the energy is reflected. This energy is reflected. Part of the energy is absorbed and released through thermal energy or fluorescence. Also, we have also a scattering of the light. If we have, for example, like some particles there, and we have a transmitted light. The photothermal energy that is in the medium create a photothermal element there because you change the refractive index of the medium because we have change of the temperature. All these processes are related through this equation. We know this very well, that the power incident to the sample can be divided. Okay, we have the incident power, the scattering power, the transmitting power, and the thermal power. And of course, the reflected power that in most of the cases is neglected, okay? Then we can have this, that all the energy that we have in this medium should be equal to 1. If we neglect the scattering, if the medium is free of scattering, we have that the thermal energy is equal to 1 minus transmitted energy. And this is the absorption of the medium, or the absorbance. But the advantage of thermal lens technique is that we are measuring directly this thermal energy. On the contrary, in UV-vis spectrophotometry, we measure also the fluorescence and the scattering. And we measure all the energy in the medium. And we don't know which part of this energy is going to fluorescent or thermal energy. Now, let's we understand the photothermal process, okay? First, we have optical excitation. This energy is absorbed, as you know, depending on the process, 10 to minus 6, 10 to minus 9, depending on the medium we have there. And we have non-radiative relaxation, okay? This energy increases the temperature of the medium, few degree, 10 to minus 3, 10 to minus 4 Kelvin. And then if we have a liquid, you know, in a liquid, and if we have a Gaussian beam, like in this case, this is a typical example of thermal lens pump prop technique. The excitation beam supposes a green laser 532 that is Gaussian beam. This Gaussian beam has this distribution. The intensity at the center of the beam is higher and decreased through the tails. Then we have the same temperature distribution. And as the temperature at the center of the beam is higher, then the molecules vibrate more strong. Then what happened? The density decreased at the center. And through the tails, we have less density. Then we have a gradient of density. And this gradient of density is proportional to a gradient of refractive index, because the refractive index depends on the density. Something similar happens in solids. But I will focus on liquids. Therefore, if we have a probe beam, because this excitation beam is periodically modulated with a chopper or with a signal generator, then we create in this very small region, because we are focusing our excitation beam in very small region, let's say 50 micron, a thermo-optical element. We are creating a lens. As the density is less at the center, we have a divergent lens. What happens when we have a probe beam of very low power, a helium laser we use commonly? This beam will suffer phase shift or deviation. This beam will diverges, converges, diverges, converges. And if we add a detector here with a small pinhole, 1 millimeter pinhole or 500 micron pinhole, to this detector, we will have that when we excite the sample, the beam diverges, less intensity arrives to the detector. When the medium is not excited, the beam comes back to the normal position, the intensity reaching the detector is higher, then we will have a signal. In some cases, if the detector size is very small, around 1 millimeter, we don't need a pinhole, and we will have also a signal. And this signal will be something like this, okay? When we excite, the intensity starts to decrease. And we measure this value. The thermal length signal is defined like the intensity when we have excitation minus the intensity without excitation, normalized to the intensity of the normal beam without excitation. This equation you have here. And we have this relation, very simple relation. We will see another model after that we develop, in which the photothermal signal, this signal that we measure at the oscilloscope or locking amplifier, is proportional to the power of the excitation beam. Of course, more photon, higher signal, but also to the absorption of the sample. Because if the sample absorbs more, we have higher release of this heat. But also we have here the wavelength of the probe beam and the so-called thermo-optical enhancement factor. What is this? This is the gradient of the refractive index with the temperature, how much, and it's a constant for all the sample. The refractive index change with the temperature and the thermal conductivity of the sample. This is the enhancement factor, and this is what made the photothermal signal more sensitive in comparison to the spectrophotometry. Okay? And now, we can measure the strength of this signal, and we can determine the concentration of the sample, because the concentration is related to the absorbance of the sample, or the absorption coefficient. Also, we can determine the thermal conductivity or the thermal diffusivity of the sample, as we will see after. Because if we fit with the model that I will present after, we can determine also the thermal diffusivity and the thermal conductivity of the sample. Okay, now I will explain you why the photothermal spectroscopy is a very high sensitive technique. Look at this. One example. If we have a drop of water, 1 microliter for example, and we consider also the beam is illuminated the sample continuously, one atom will absorb, okay, photons, and will release the energy thermally. We know that this time is of the order of 10 to minus 9, 10 to minus, depending on the sample, okay? However, the photothermal process is very slow, 10 to minus 3 milliseconds. It means that In the meantime, we are exciting the sample. This photothermal energy is still there. And this atom is excited, emit, excited, emit again. And the signal is increasing. This depends on this ratio, the lifetime of the atom and the photothermal process. It means that we will have around 10 to minus 8 emission of one single atom during that time. But this is not the only condition. We know that the photothermal process is a phase, this is a phase method. The phase, as we studied here before from the other speaker, the phase is related to pi L, the length of the sample, and the wave of the probe beam. And, of course, in photothermal, we have the thermo-optical factor and the variation, the change, the rise in the temperature, okay? What happened? Here, we have a cell commonly of 1 millimeter, even 1 centimeter. But the wavelength of the probe beam is around 10 to minus 9. It's nanometric. This is a large ratio. If you divide centimeter by nanometer, this is very large phase shift. And this is the reason why the photothermal spectrophotometry, that is also an interferometric method, is high sensitive. We have two facts that demonstrate this. High sensitivity. Okay. What happened? Okay. Now I will explain briefly the theory. Behind this equation, there are a lot of calculations that, of course, I don't want to look at this now because this is very well known. We have to solve the heat diffusion equation first. The heat diffusion equation, in which we have here the temperature rise in the sample. We have the thermal conductivity, the heat capacity, the density of the sample. It's a very well-known equation. And in this, we have the source term, the excitation, the pump laser. This is a Gaussian distribution. Commonly, we have a Gaussian distribution, okay, in the laser. As we know this very well. If we solve this equation, we know that we will have the temperature rise in the medium that has this expression. Depend on the, depend on the power of the excitation beam and the absorption coefficient of the medium. Okay, here we have also the heat capacity, the density, and the radius of the excitation beam. Okay? Here also the time and the characteristic time of the thermal rise or the thermal length signal. That depend on the radius of the excitation beam and the thermal diffusivity of the sample. We know that we have the refractive index depend on the temperature in that way, but we will consider only the first approximation. We have here the refractive index in the radius and in time dependence. This is one example for ethanol, the values. This temperature increase create a phase difference that we can express through this equation. As we know, the refractive index around the axis and the refractive index at the axis. We have a gradient of the refractive index in the axis and in time. We have two dependencies here. After that, we have the phase shift of the probe beam, okay? And we have this theta here that is proportional to the power of the excitation beam, the absorption coefficient, and the length of the sample, or a cell if we have a liquid, and the photothermal parameter that we already knew before. With this, of course, alpha L is the absorbance of the sample. It's the same. Now, if we have a probe beam and we have a sample in which we create a photothermal lens element here, this phase shift is added to the field of the probe beam. As you can see here, it's distorted by the thermal lens. And then the thermal lens signal is defined as the signal through or the transmittant of the pinhole at the detector when the thermal lens signal is not present, when we don't have excitation. And this is the thermal lens signal or the transmittant of this small pinhole when we don't have excitation. This transmittant is defined here, as you can see there. This is the radius of the pinhole. This is the electric field, the square of the electric field. You know it's the intensity, okay? And then we perform calculations. This is very long calculation. You can see in our papers this. And you reach to this equation in which we have the value, the amplitude of this thermal lens signal that, as you know, is related to the power of the excitation beam and to the absorption coefficient. And we have this arcotangent here that is a geometrical factor. We have the mode mismatch between the beams. This is the ratio between the probe and excitation beam. We have theta here, phi naught, and the Rayleigh parameter of the probe beam, and this is a geometrical factor that depends on the length L, that is the length between the sample and the detector. We have the Rayleigh parameter of the probe beam, the position of the waves of the probe beam, and so on and so forth. Then, this is the equation that usually people use for calculating the thermal lens signal. Generally, people, they do a calibration because you have to measure all these factors experimentally. It's very tricky. It's a little difficult. And of course, you can do it, but the uncertainty of your measurement increase. Or you can do fitting using this equation, and you can extract the thermal diffusivity of the sample that is included here in this TC, as we saw before. Okay, what we did, let's first speak about the conventional thermal lens setup. There is mode match in which both beams are focused onto the sample in the same radius, and the mode mismatch configuration in which the probe beam is highly collimated and the excitation beam is highly focused or focused. Under this configuration, we demonstrated that, and this is the Rayleigh parameter of the excitation beam. The Rayleigh parameter is this distance, is where the radius of the beam increased twice, but also is related to this equation. Okay, if we use this equation and we simulate this equation, for example, we perform C-scan. You know C-scan, you move the sample around, when you have focus excitation beam, you move the sample around this position. Of course, this is for mode match using water as an example. This is the thermal diffusivity of the sample, and these are the experimental parameters we use in this setup. And we have mode match, mode mismatch. The difference is that here both beams are focused onto the sample, and here the probe beam is collimated, the excitation beam is highly focused. We can see here that we have a valley peak, and the amplitude of the signal is lower than here. It means that the mode mismatch setup is highly sensitive, more than the mode match. I will explain you after why. This is theoretical simulation. It means that if we perform this kind of experiment with a highly collimated probe beam, we will have higher signal. A very simple example. If you excite, example, you create a lens. The lens will be 5, 50, or 100 micron, depending on the size of your excitation beam. Of course, you have thermal diffusion. This length will be a little higher, depending on the thermal diffusivity of the sample. Let's say around 400 micron. If your probe beam has the same size that your excitation beam, then when this length increase because of the thermal diffusion, your probe beam only will be sensing part of this temperature field of this thermo-optical element. However, if your probe beam is wider, is collimated, you will sense the whole temperature profile. It's the same in conventional optics. If you have a lens and your beam is passing through the center of the beam, no distortion of this, no phase shift. But if your beam covers the whole numerical aperture of the lens, you will have maximum deflection. And you will reach the diffraction limit. It's the same here. And this is why we propose to have a collimated probe beam. We demonstrated numerically with simulation that this is the maximum signal. Why? If you have an arcotangent, as we have in this equation, you know that arcotangent has the maximum value is pi over 2. How you can reach this value, pi over 2, that this is the maximum value? There are some experimental conditions in which you can manipulate and reach this value, pi over 2. And here you can see, if we make this a constant, pi over 2 will be very easy using this equation to calculate the absorption coefficient directly. And we don't care about any experimental parameter, okay? And this is what we propose here, making the Rayleigh parameter of the probe being very large, highly collimated, larger than the distance from the sample to the detector, and larger than the Rayleigh parameter of the excitation beam. Under this condition, and locating the sample at the initial of the coordinate system, 0 position, equal to 0, and when the time tends to infinity, we demonstrate using simulation that this arcotangent is pi over 2, as we can see here. Harold, can you go ahead? Because from here it's not possible. Okay, it's okay. Okay, and when we have this, and L, we know, is larger than the Rayleigh parameter of the excitation beam, of course, this value is very large, and the arcotangent then, because the arcotangent of infinity is pi over 2. We demonstrate this doing by hand calculation, also using simulation. Okay, and we reached a very simple equation in which we have the thermal length signal that you can measure experimentally very easily is proportional to the power, and all these parameters are very well known for any sample, and then you can calculate the absorption coefficient. But we demonstrated this also. With this experimental setup, we have here the excitation laser. We modulate this laser at a specific frequency, and we excite the sample here. In this case, water. We use water to demonstrate this system. And then we send a reference signal to the oscilloscope. We create a thermo-optical element. We remove the excitation beam. We don't need more the excitation beam. We use the probe beam collimated with this telescope system in around 2-3 millimeters, and then a pinhole and the detector. And we measure here the signal, the thermal length signal. And what we have this is the experimental results. What we did before with theory, we demonstrate also here. You can see here that the signal reaches the maximum value and is always constant because this value is very low. It's highly focused excitation beam. And in this case, we have highly collimate probe beam. These are the experimental results and fitting with theory for different Rayleigh parameters of the excitation beam. You can see that there is not any change. And this is the maximum value of the signal. Of course, if we go further, this signal starts to decrease because we are not reaching pi over 2. After this, we go to the experimental verification, okay? We want to measure any value, the absorption coefficient of water at 532 nanometers, because there are a lot of reports about this value. And we have at the oscilloscope, the signal we process with the equation that we know, and we can do fitting. You can see here the fitting. We can extract the thermal diffusivity of the water using the very long equation, but also we can measure directly here, because this is pi over 2, the absorption coefficient of water here. Okay. The absorption coefficient of water, that is 3.4, 10 to minus 4 centimeter to minus 1. Of course, what we did is to use different powers. You can measure directly, but in order to reduce the uncertainty, you use different powers. The signal at different power, we have this linear relation, and the slope, we also can use the slope of this, because it's the same equation, to have higher precision. But you can measure only with one value of the power. It's the same. It's only to reduce the uncertainty. Okay? After this, we compare the results with very well-known reported results. You can see here using the different techniques, but I have to tell you that these are very, let's say, bulky techniques, because they use very long cells, meters of cell, using spectrophotometry, using different techniques, and you see that this is very good agreement. Okay, after that, we go to the applications. The first application is related to miniaturized gel electrophoresis with thermal length detection. Which are the advantages of gel electrophoresis with thermal length? For the first time, we demonstrate this because if you miniaturize on a chip and you couple with thermal length detection, you can separate a wide range of materials, because in thermal length, you can concentrate your excitation beam, your probe beam, in very small region. On the contrary, in normal slab gel electrophoresis, you use a tank, you add your sample, you add the voltage, and then you see very wide broad bands. And the only way to elucidate the difference is with a picture. But this is very hard. It's not precise. When you have a small movement, it's also very hard to determine this. You reduce the sample volume. You can have parallelization, different device for measuring even the fluorescence if you want. Harry, tell me how much time I have. I started at 20. Okay. The analysis is shortened, okay? Takes advantage of the increased spatial and temporal resolution, because you focus your beam. And you can detect fluorescence if you have fluorescent samples, okay? In thermal length spectroscopy, we can use two setups. The conventional setup, you put here, you introduce from here the excitation and the probe beam, focus onto the sample. This system has some disadvantage. We demonstrate that if we use a collimate probe beam, the thermal length microscopy has some advantages. The first one is that if you use the collimate probe beam here onto the sample, you know already that it's more sensitive. Also, it's easier for alignment. In this case, you have to use very specific microscope objective because the position in mode match spectroscopy, the position of the probe and excitation beam, they have to be at very, very precise distance. That is square root of 3, the Rayleigh parameter of the probe beam. In this case, you don't care because the probe beam is collimated. Then we propose this setup, and this is the setup that we use for gel electrophoresis here, miniaturized. You can see here. The excitation laser, collimated, come here, and you have a mini chip here. We develop a mini chip here, come here, and the probe beam is coming counter-propagating here through the sample, through the microscope objective, through the detector here. And we have the power supply here, it's around 100 volt, very low voltage, that we apply to the sample here, okay? Okay, looking amplifier, if we want to amplify the signal, if the absorption is very low, the signal generator, the computer, and the rest of the elements similar to what we saw before in the previous setup. Then we apply this first to monitor the Fe3O4 gold core shell synthesis. Why? Because during the synthesis process, we need this, people use this for biomedical application. You need all your particles to be covered by gold, but this not, most of the time it's not happening. And then you have to check this. And the way to check this is what we propose. Here, this is the mini chip. The mini chip, we apply here the voltage, positive, negative voltage, and this particle negative charge, we introduce the particle here, okay, and they will come to the positive charge. Then, when they pass through the system, thermal length, where we have the excitation and the probe beam, you will have a signal. For example, this is the particles without gold, and we have this signal. And we have a system that detects automatically the time, the retention time, and give you the peak when the particle passes. This is very, very short band. Then we characterize the retention time, but also the intensity that is proportional to the concentration of the sample. And then we go to the synthesis process, and we can see here that we have this peak that are the particles without shell, and these are related to gold, okay? We can see that not all of them were converted. It's very easy because they are separated, because they have different size. And inside the gel, when you apply a voltage, they go faster, smaller. And the bigger, they go slow. And you separate. Because of that, we characterize using 10 transmission electron microscopy in order to have agreement between these. Of course, this is a very expensive technique that we use only to demonstrate our system. You can see here we have two populations of particles. You can see also here the histogram, the two populations of this approximate 10 or 25 nanometer size, confirm that, of course, we have the two population of particles there, and that what we are detecting. Also, we did elemental analysis, and we saw that in this elemental analysis, we have also these big particles, small particle without gold, and we have gold in these big particles. Then, because of the shell, okay. We compare here the results with conventional gel electrophoresis that, as I mentioned before, you cannot see the difference between these two bands. It's impossible to see in this, and you use very, 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 very large volume. And you have to apply during very long time this voltage. And we also did monitoring of the DNA gold nanoparticle surface coating. the surface coating is very important for biomedical application. And then a group in Electra working on this, they needed to know, because there is no way to know, where is the best surface coverage of this DNA on gold nanoparticles. Then the way to know that, you can see here, for example, with UV normal spectrophotometry, you cannot see the difference in the peaks here. Here is because of aggregation, aggregation of the particle. And here we have different ratio, gold nanoparticle DNA. 100, 300, 400, 500. This is the ratio of this. Here, this is let's say, to see that it's impossible to see that this, we reproduce this part here, okay? And the first things we do with it is to have a calibration curve of different concentration of these gold nanoparticles to see if the thermal lens system is able to detect. And we saw, yes, we can detect this. It's linear, the dependence. Then let's go ahead to do electrophoresis with the system. And we can see here, these are the results. For 300 was the best surface coverage. What happened? When you have the optimum, this is the band. You can see here, very, very narrow band, less than 1 millimeter. You can see here, 300. This is, cannot see very well here. Okay, we start here. 100, 200, you start reducing the retention time. But when you reach the surface coverage, that is 300, you have the optimum, the whole surface coverage. After that, you start adding DNA, but they are not coming to the surface, or they are increasing the size of the particle, and then they start again to delay, as you can see here. But the most important is that we determine 300 is the best and complete surface coverage. As you know, DNA, they are negative charge, because of that they move from the negative to the positive, as you can see here, okay? This is the band moving here, okay? And this is a conventional slab gel electrophoresis. You can see here, you cannot see any difference in this picture. And because of the high spatial resolution of the system, thermal lens system, you can detect there, okay? Then, if I have time, I want to finish. What we did also, we couple thermal lens with interferometry for the first time, because, you know, you are sensing in thermal lens with a probe beam because of the intensity variation at the detector, that is silicon detector. However, this is an indirect method. This is not direct method, because what happened, or what changed in the sample, is the phase. The phase is added to the probe beam, and then the field, and the square field is intensity. It's not direct method. However, if you are able to measure directly the phase, you are using a direct method. And interferometry is a direct method. And this is what we did. We propose here to use excitation beam. It's the same setup. The same setup, excitation beam onto the sample, and the difference is that the probe beam is detected by a CCD camera, but we are doing both simultaneous. We also use thermal lens here, half and a half. And we measure directly the phase, because in interferometry, you can measure the phase, and this is what you saw in the previous lecture, that there is a way to measure this phase. I will speak a little more about this tomorrow. And go ahead, Harriet. It's not working. First of all, we use gold nanoparticle at different concentration to demonstrate the system. And we characterize with UVBs. And we have different absorbance there. Okay? You can see that the very low absorbance, you cannot see very well, because UVBs is not sensitive enough, and there is a high uncertainty. This is why we are proposing this method. Go ahead. Okay, this is a interference pattern we got on one of the sample. We have different concentration. For example, this 0.47 nanomolar, and we have the interference pattern here, and you can see the complete evolution of the thermal length. This is the advantage, that you can see the whole region of the thermal length. And then you can get, using the same procedure that the Professor Pereira explained you before. I will speak a little about this tomorrow. You process this using the Fourier transform, inverse Fourier transform, and you get the phase shift of this phenomena on the space, in the space, okay? I will show you now for this sample. You can see there the profile, okay? This is the experimental, and this is the theoretical that you saw before in the theory. You can see that this is a very good agreement, and from this, the fitting parameter is theta, and theta, you know, is related to the absorption coefficient or the concentration. Then, using this, we calculate. We can use only one value, but we are demonstrating that there is perfect matching, perfect agreement. But you can use any radius here related to this phase shift, okay? And then we calculate the absorption coefficient for all the samples and also for water. This is for ethanol, excuse me, for ethanol. And we compare with the previous results, UV measurement, of course, the high measurement, because UV is not able to measure at very low values. And we use also for water. Go ahead. Okay, we also build a calibration curve to demonstrate that this phase shift is linear, and we determine also the low detection limit. Go ahead. We did the same for water. You can see here the profile, the phase profile, and the fitting procedure. Go ahead. Okay, finally, I will, I think we are a little late. The conclusion are that first, we miniaturize the system, and with this, we increase the measurement time reduce. We also reduce the volume of the sample. We increase the uncertainty was decreased. In the case of the application in miniaturize. Going to interferometry, we saw that also the method is direct, is very fast, and you reduce the error in your measurement. Related to the setup, you can see that the Collimate probe beam make you a more reliable and precise system, because you take advantage of the whole temperature field of your create thermo-optical element. With this, I want to conclude, and tomorrow I will continue with the application. I will speak a little tomorrow about LED instead of laser. We are using LED for excitation, and I will explain you why it was possible. We introduced also a new method for increasing the sensitivity, and I will speak a little about digital holography microscopy. Thank you for your attention.
Thank you, Dr. Ambato. My question is about when doing photothermal spectroscopy, one of the limitations is the generation of heat when using the sample. How do you put this limitation into consideration so that to obtain the correct results?
It's not a limitation. The power we are using is very low, 10 milliwatt. the temperature rise onto the sample is 10 to minus 3, 10 to minus 4 Celsius. This is very low. There is not convection. If you increase the power too much or your sample is high absorbance, yes, you can have convection effects and all this equation will be distorted. It's an advantage to have because if you have a sample, this is what I will speak to more. If you have a sample that at the same time has fluorescence and thermal relaxation, you can measure both at the same time, and you can measure the quantum efficiency of photothermal conversion that is important, for example, for phototherapy of cancer. And the system gives you additional information. You cannot have this with UVBs, for example. But the question is to go low power to only increase the temperature of the sample at the very low value, not to have convection effects.
Hi, Humberto. Great talk. My question is related to any link between this photothermal imaging and photoacoustic. Because in photoacoustic, we generate a pulse, a very short duration, to create thermal expansion, and then you image that. So is there any relationship between these two imaging modalities?
Yes, I did in photothermal imaging, yes, but photoacoustic is mostly used for photothermal imaging. In thermal lens, I saw few words related to photothermal imaging, but photoacoustic is most better in this case because of many facts. Because you are detecting the whole photoacoustic field, and you can detect the scanning is faster. In thermal lens, you have to have a very fast scanning. But yes, photoacoustic is better for imaging. It's less sensitive, but it's better for imaging. There's another question there.
My question is regarding the Z-scan measurement. And you could show the valley-peak relationship. Does that give you information of whether the material is positively thermolensing or negative, depending on peak valley or valley peak configuration?
Yes, exactly from this peak, you can determine if the material is negative or positive. If this positive, will be like this. Negative will be like this. And also, if you determine the amplitude of this, is also related, doesn't matter if negative or positive, give you information about the absorption coefficient of the sample, and also the nonlinear parameter. Like nonlinear refractive index, for example, can be calculated using this. Exactly.
Any other question?
Online?
So thank you, Roberto, for that wonderful presentation. So about the mode matching, I'm wondering how do you ensure that you are actually able to match? Do you do mode locking?
No. This is only related to the size of the beams onto the sample. We measure the size of the beam. In mode match, what we try is both beams to have the same radius onto the sample. They are focused using the same length, and they are focused in the same side. In the case of mode mismatch, the excitation beam comes separately, excite the sample, focus, and the probe beam is divided here by a beam splitter, as you saw there, and is completely collimate. And we measure the radius of the probe beam over the excitation beam, and this is the degree of mismatching. It's not related to that. It's very easy procedure, though. It's a definition in thermal length. It's different to that.
Let us thank the speaker.
Thank you.
And now we go for break. Then we come back at 10:15.
Expanding the horizons of all. These belong to everyone.
So let us be back at 10:20, please.
Theoretical physics has a unique mission that supports science is the common heritage of all of humanity.
Can you
The center supports researchers from less advantaged countries and works to remove barriers they may
maybe
face.
here, no?
Here, everyone speaks one common language, science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
We are all looking for something. Some of us search for a treasure, some for inspiration, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University of Kenya ICT Museum, the only one of its kind globally. Visit the main campus and be taken through the telecommunication evolution journey. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all of humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language, science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT,
Check.
and business
Si tunaweza?
studies.
Siko live. Check. 2. Test 1 2. Testing 1 2. Testing 1 2. Check.
That offers editing skills and use of iMac computers with various video editing software such as Final Cut and many more.
Check 1 2. Testing 1 2. Nime bump up to -6. Check 1 2. Testing 1 2. It's now 0. 2 1 2. Testing 1 2. Testing 1 online. Check.
This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issue. This is our physics and chemistry lab, where most practicals happen, including tests on materials and present research findings to scientists, ensuring safety and quality standards are met. This is our computer lab, also known as Korea lab. This is where computers classes take place and most of the computers are installed with internet. welcome to our radio. We have our own radio station that provides information to the citizens and people at Gatarongai. Listen to the sweetness of our radio on 99.9 FM and learn more from our students as they bring to you hot shows. This radio has greatly helped students acquire communication skills in readiness to join national and international radio stations.
Two, 1, 2. Check.
A laptop is an essential asset in the modern society. However, many of them are lost as a result of theft taking them vital information. But now comes Electraca, an online system that gives users the ability to register various electronic devices using their serial numbers. To access Electraca services, visit the website, create an account, log into your account, register the device serial number. In case your device is stolen, you report in the portal. Electraca will then help you track and recover the device.
Hello, my name is Patricia Mativo, and I'm a student at the University of Oxford. But for my undergrad, I went to Multimedia University of Kenya, where I pursued my bachelor's degree in analytical chemistry.
Hi, my name is Ndera Sikindiri. I'm currently studying a master's program in chemistry at the University of Gordon by student with a scholarship from the student. My journey began here at the Department of Chemistry at the Multimedia University of Kenya, where I pursued a master's program in industrial chemistry.
Hello there, my name is Ambassador Anita. I am a graduate student at Multimedia University of Kenya, taking Master of Science in Analytical Chemistry. I'm also a scholar under the Stipendium American Scholarship at the University of Crete in Hungary. I am taking a Master of Science in Chemistry, specializing in research.
I must say it's thanks to the family and the community around the department and the faculty at large that made me who I am today, a transformational leader.
And if you told me I would be where I am today, I would probably tell you of luck. Because my journey at Multimedia University of Kenya has been nothing but transformative.
I've been able to work with various agencies and the government. This is because I was not only taught to become a chemistry student, but also to become an all-round discipline student, where I was able to bring in solutions for our modern world challenges.
One notable thing about Multimedia University of Kenya is that it offers the resources for you to grow as a student.
And this is why I think it would be important for you to consider applying to the Department of Chemistry, or either your undergrad or your postgrad.
Whether you're considering an undergraduate or a postgraduate studies in chemistry, I would strongly urge you to consider Multimedia University of Kenya, which will shape your path to a fulfilling future with the academic experience. Join us today and embark on your own journey towards an achievement.
Yes. Screen is visible. Can you speak?
So you don't want anything that is reflective on your hands, not even a watch, because otherwise you might have reflections that you are not controlling, and it can be dangerous. Okay. Right now, as I said, this one is not an hazard, but in general, it's very important that you work in a safe way. Let's take our cylindrical lens. So I'll show you this one. So this is a cylindrical lens. Maybe you can have a look. So you see, I don't know if you can see what I want you to see, but here it's flat, okay? This side, can you see that it's like a cylinder? All the effort, can you see that it's curved only in one direction. You can see, right? Okay, it should be quite obvious. Can you see? So, the thing is also, you would say, well, just clean it. It's not that easy to clean it, huh? You need the cleaning tools and then specific products. And sometimes some of the optics have coatings that you can damage if you clean. Okay. So, for example, if you have a dielectric mirror like the one that we were talking about today, when the other lady that was talking about compression with the dichroic mirrors, with the multi-layered mirror, those mirrors are really expensive. You don't want to get them, like, you don't want to touch them. You just stay away from my dichroic mirror. And if you try to clean them, I mean, you might ruin the compression of your pulses. So it's really something that you shouldn't do. Well, now it's done. Yeah, exactly. So I'll show you. So if I mount here this lens, okay, this mounting that I have placed here, it is a mounting that can rotate. Okay. So let's see what happens. Okay. First of all, let's check with a piece of paper. So we check in a controlled way. So I'm here. I'm very close to the lens, and there is nothing to see. But if I go in the focal plane, look, I have a line. Can you see? So the focal plane of this lens, it's a spot. It's a single dot. Here, the focal plane, it's a line. Okay? Why is that vertical? Here it was round, here it's round. Here it's horizontal, and over there it's vertical. First of all, if we think of this in 3D, it's a plane. Look, you can see the plane if I do this. Can you see that it's a plane? Okay. If I rotate the cylindrical lens, so I'm rotating it, you can see I can rotate the beam. Okay, now it's vertical. If I do like this, you can see even better, probably that this is a plane. Can you see? Okay, in the other direction now. Okay, so if I rotate while I move, you can see it nicely. I have a trick. If I have time, I will show you my trick. My trick is use, I'll show you later. Yeah, it's a nice trick though, so I want to show you. Let's go on. How large it is here in the focus? Somebody can read. No, are you sure? Okay, so then you tell me, okay, so how large was it here? No, then it has to be the same. Because what the cylindrical lens does, it squeezes in one direction, but the other one is left untouched. So the height of the beam, it's the same. Because it doesn't do anything in one of the two directions. So now let's look at the propagation. What do you think is the thickness here? It's 0.7. Do you want to check? Want to come and check? So you have to say that it's 7. No? It's 7.
It is 0.7.
Yeah, it's 7. Otherwise, physics doesn't work. This is a 10x objective. It will magnify 10 times. And it has a 0.28 numerical aperture. Do you think this is a large number or not? It's not. It's not. A good 10x is 0.4, usually. At least 0.3. Come on, this is 0.28. Why? Well, this objective has the pro, it has a good point of being long working distance. So the focal length, it's very long. So this gives me the opportunity to mount in a three-dimensional manner my sample. So I have space. I don't need to stay here very close to the objective. I can have something that is very big. If my sample is 1 centimeter, I need to be able to move it around, for example. So I want to have room. If I was using a very high NA objective, I would
Vikas, can you speak like a couple of sentences to check the voice? Yes, yes.
Okay, okay, so yes, yes. So my name is Vikas, and so I will be going to talk about AI-driven biomedical imaging for smart diagnostics. So can you hear me now? Sure, sure. Take your time.
Recording in progress.
Yes. So hi, my name is Akash. Can you hear me now? Is it better? But I hear some echo from your side. Actually, there's something else going on as well, right? Okay, thank you, thank you. So can you hear me now? Hello, hello. Okay. Okay, so yes. So can you hear me now?
We are getting you.
Am I audible? Like, is it my? You can hear my clear voice?
Yes, we are
Yes,
getting
we.
you. Uh, also, your microphone, we are going to check.
Hello. Uh, Welcome back, everyone. So this is like second session for today, and I will be obviously chairing this session. Our first speaker over here is Dr. Vakas. He's working as an assistant professor at Information Technology University. He did his PhD from University of Florida, while master's was from Seoul National University. Uh, his PI of Intelligent Machine Lab, and his research area includes computer vision and deep learning. And he has published several papers in reputable venues, including CVPR, IIIA, etc. He's also recipient few very prestigious awards like Google Research Award in 2023 and Facebook Computer Vision for Global Challenge in 2019. So he got these awards for developing low-cost solutions for efficient malaria detection, particularly in Pakistan. And today he will be talking about AI-driven biomedical imaging for smart diagnostics. So the session will be like he will be talking for 1 hour, roughly for 55 minutes, and there will be like 5 to 10 minutes Q&A, and then there will be a second lecture, and again followed by Q&A. So over to you, Dr. Vakas. Thanks.
So can you hear me? Can you hear me? So can you hear me? You can start now. Okay. So I can so I'm going to start, right? So I'm audible. Just want to confirm. Okay, okay, great. Okay, great. So first of all, thanks a lot for providing me the opportunity to present our work and also the related work in AI-driven biomedical imaging. And I'm such a grateful and really happy to be here. So my name is Prakash. I'm assistant professor in computer science in information technology, University, Pakistan. So here is the our lab. So our lab name is Intelligent Machine Lab. We work in computer vision, machine learning, deep learning, medical vision, and remote sensing. In our lab, we have two research groups. One specifically focused on application of AI on medical imaging, and the second one is application of computer vision on different kind of applications of machine learning and the deep learning. So, and we're fortunate enough that we have been able to target the top venues in our field, which are NeurIPS, CVPR, ECCV, AAAI, and Nikai, and Becky, and all this stuff. And the right, I'm just showing off our campus building. So in our lab, we have 5 PhD students, 10 master students, 10 undergraduate students, and we are 2 faculty members, me and Dr. Mohsin Ali. So, so this is a brief introduction of our findings. We have, just a second. Assalamu So, so we have uh, uh, so we have been awarded. So the Google Research Award in 2023 for to work on low cost cancer detection, and also we have been awarded a Google Facebook Research Award in 19 to work on low cost malaria detection. Our other donors include Facebook, UNDP, Microsoft, ETRI, and obviously our Higher Education Commission and Information Technology University. So in our lab, we work on four research areas. One is remote sensing, other is medical imaging analysis, third is a video surveillance, and fourth is a UAV analysis. So the analysis of the video that we got from UAVs. So because I believe there should be lots of students here. So what I'm going to talk about here is mainly will be on my Google Scholar page. So I would request for the students to take the picture of this page and send me an email if you have any questions. You see if we have joint interest of working on some joint collaborations, and if we want, we can work together. If we can help you in something, if you can help, you think you can help us in something, so please do send an email over here. So please do take the picture of this page, the screen, and send me an email. So I will just wait a couple of seconds so that the students can take the picture. Okay, so basically, in the medical imaging analysis, we work on cancer and also the malaria mainly, and then we also have worked on the retinal image enhancement, and then the detection of human health from the face, and also the projects related to the blood cancer, the skin cancer. So in today's lecture, I will be first giving a brief introduction of our work in the medical imaging. Then I will describe about the general topic of machine learning in object detection and its general applications. And then finally, I will give a detailed introduction of our work on malaria and cancer in peripheral blood slides. So in the last part of the work, I will show you some applications and some results of computer vision and deep learning on the images which are taken from through the mobile camera mounted over the microscope. Okay. So let me briefly go through the mm, the the work that we have done in the medical imaging that and the recently. So so first of all, why we got interested in the medical imaging is because in the developing countries. So in the developing countries, people observe poor health facilities. We think that people observe poor health facilities due to the three main reasons. One is unavailability of expensive medical instruments. Then there's a lack of doctors who can spend sufficient time to analyze the outcome of the and then the digitized data. So first of all, the medical instruments are very much expensive, so it's not easy to afford them remote areas specifically. Then not all the well professional doctors are available at all the centers. So the good doctors usually go to the developed world, and so we don't have very good quality doctors in all the areas. Thirdly, the several of these medical diagnostic work is not documented. So there's no digitized data so that other junior doctors can build on that. So there's a really need of having to digitize the images and the data that we are getting from the microscope so that we can all share the knowledge and help improving each other. So according to the statistics of World Health Organization, there are very few number of physicians available for every 1,000 people. So it is alarming. So we really need to have AI-based solutions that can help people in the real-world applications and they help in diagnostic. So because to relieve the burden. So one thing that I would like to enforce here is that so the purpose of medical image analysis and AI-based diagnostic is is never to be eliminate the doctor or the X-rays. He also looking at the patient. I mean, he also had the history working for the specific yeah. So sorry, I get disconnected for a while. So I will continue from there. So what we were discussing that that there's a huge market for the medical imaging projects because there are a lot of populations, a lot of areas which needs to be addressed. However, the product doesn't necessarily to be get approved easily, and the reason is that we need to really it's a really challenging because your product in effect human life. So there's a very tough criteria to get approved. So, so basically, when we say biomedical imaging and analysis, we are talking about understanding, visualizing, and quantifying the information. So basically, you want to understand what's going on in the image, then you want to put into the some visualization, which are useful to the doctor, and then you want to quantify the information there to the level which may not be that easy for the doctor to get quantified. So basically, The medical image or AI-based smart diagnostic is a merger of different technologies like computer vision, machine learning or the deep learning, imaging sciences like radiology, image processing, and finally medical image computing. So when you say that you are progressing, you are progressing some images, so using for your AI, you mean that you are using computer vision, deep learning, machine learning, imaging sciences, image processing, and all this stuff. So when you talk about images, so what we see is basically a different patterns. We see, for example, here below you can see that it is an MRI image, and there's a small region there. But what computer sees is just the numbers. So for computer see is a 0, 3, 2, 5, 4, 6, 7, 8, something like this. So what we need to do is we want to extract some very useful information from these numbers. So this is a real challenge. So, but the computer C is just numbers, and we want to get sense of those numbers. We want to increase or improve the better visualizations, and then we want to quantify it better. Okay. So the medical imaging are different from the different natural picture, because, for example, when you go to the market, you take your pictures. When you go to the birthday, you take your pictures. When you naturally take your selfie. But the motivation for and the application and the algorithms which will be going to use for the medical imaging will be different from the other pictures. So, because the medical image depict distribution of various physical features which are made from human body or animal. So you just don't want to show the mountain, for example. You really want to see if there's a X-ray of the human body. Then what does it actually mean? And the picture should really make sense of the distances and all this stuff. So, uh, so then basically the analysis of biomedical images are guided by very specific expectations. Okay, so you want to have the automatic detection of tumors. For example, you want to characterize their type. You want to have the measurement of normal and abnormal structures. You want to visualize anatomy, surgery guidance, therapy planning. So, so you want the the algorithm to give us the automatic detection of different kind of tumors, how they are classified, and then they have a normal structures. And then while you're doing the surgery, these things should help you, and also they help us exploring the relationship between clinical, genomic, and imaging-based markers. So, because what we see in the image is, for example, an organ, but in reality, the dimensions in the image are very different from the dimension in the real world, right? And for example, we put cursor on the image, but that cursor actually is just one point in the image, but actually it corresponds to a different location in the human body. For example, for example, size of the in reality, what is the actual size in millimeter, or micrometer, or the nanometer, or something different. For example, in the case of tumor, you really want to get the exact size. So medical imaging can help in that. So basically, medical images allows doctor to find the diseases in the early stages, better outcome for the patient. So doctors can help. They can help in more accurate measurements. We can help to detect, for example, cancer, breast cancer, pneumonia, and other diseases. And there's a well-defined research that if you are able to do early detection of several diseases, you can drastically reduce the number of deaths. So also they help in assisting in the future decisions regarding treatment, regarding the future care of issues, regarding the medicine you want to give it. So for example, if you just an that's an example to motivate you. You could look into in the microscope and the blood slide, and you think there is a 25% of abnormal white blood cells. But the AI algorithm can give, and then you give a patient device medicine to the patient, and you come again, and you saying, oh, it's still 25%. But the AI can give you exactly like whether it's 21.2 or 25, whether the previous medicine have some impact on the white blood cells or not. It is basically help doctor in having a more accurate decisions. So basically, just to summarize, when we say the medical image analysis, you want to improve the image quality. Whatever you see, for example, you see the retinal images, you see microscopic images, because the hardware is fixed. You have some lens, some optics, whatever it is fixed, right? So, and you have very expensive things, you have a better quality visualizations. But what to do after that? So, for example, can you improve the image quality once once the image is captured from the low cost device? So can you do that? For example, can you help in improving the super resolution? You improve the quality just in the software. Obviously, when you improve the quality, you have to take care of the medical stuff. You cannot introduce some new images. So, for example, in the fake video generation, fake image generation, for example, you can generate whatever you want. But in the medical imaging analysis, it's very constrained environment. So you have to be very, very careful. Then when we say that medical image analysis, it should be helping us to classify tissues and cells. Otherwise, it's kind of no useful. Then we want the medical imaging analysis mean semantic description, understanding of the whole picture of the image. So when we say medical image analysis, we really want the algorithm, either it will be improving the image quality, either it will be improving the tissue tissue or cell classification, or it will be help us to have a better understanding of the image. Okay, so this is all is possible using machine learning, computer vision, medical image analysis, and medical image computing. So this is a whole area which actually, once given the image from the microscope, you want to improve it further so that you can have a better understanding. And the reason why you want to do this, to have once, for example, you capture the image, you want to improve the quality. Second, you want to have the better counting of the cells and the tissues. Third, you want to have the better understanding of the whole structure of the X-rays or something else. Okay. So to give you an example, for example, this is a liver lesion, and a doctor was told to mark manually. Okay, so if you see here is that so these images, these annotations, and the doctor actually annotate these images after 1 week. So you see there's a huge difference between the within 6 weeks, the same doctor, exactly the same image, but he's producing different annotations. So for example, he's declaring that on the upper left here, we think that is not a cancer here, but in the after 2 weeks, he is considering that a part of the cancer. So he's removing here some normal tissues as well. But in the first picture, he is ignoring some abnormal tissues. Okay, and from here as well. So when you, for example, for the laser treatment and all this stuff, when you rely on the doctor calculations. So he might be able to remove the um, some useful tissues and the useful cells, and other way around he might want to be try to be more accurate, and then he tried to get rid of he maybe ignore the some potential cancerous regions. So because human are observations vary time to time, but AI and machine learning are whenever you to the machine learning algorithms, whenever you give this image, it will always produce accurately exactly the same image. So the given the same algorithms, if you give the image right now, it will produce one results. You give it after 2 weeks, it will produce exactly the same results. You give it after 10 weeks, it will produce exactly the same results. But if you give it to the human, so his observations is depend on the what he think at the time he's doing the annotations will vary a lot. So this is a very clear example, like why we should be using medical imaging and why should be should be doing this. Okay. So um, so from now onward, I'm going to talk about our recent work on different medical imaging applications. So one of the stuff which was about out of distribution detection in malaria and skin cancer images. So the motivation is that what one of the issue with the AI based solution, you train an AI based solution on the malaria and the skin cancer, for example. So, and you happen to have some images of some other disease, which is not of this type. So your AI system still predict, consider them as one of the type of cancer. Because in AI and in machine learning, the traditional way is that you, given the image, you classify into the specific type of classes. For example, there are 10 classes of cancer. Then whenever you give one specific image, it will classify them into one of the type. So one of the 10, it will always say one of that type. But for example, you happen to have some 11th type of cancer, which your system has never seen before. It will not be able to detect that this is something which I have never seen before. It will still classify into the one of the 10 type. So this is very, very crucial and very, very uh, alarming that AI can never tell you. It is very difficult to get decision from the AI that I'm going to fail it. So I don't know. So it is very difficult to get information from the AI system that he don't know, because he always says you something. It will give you some results, and then it's up to the doctor to analyze those results. So one paradigm is that we want to say that given the method, and you want to say like the AI system should tell us that this is something it has not seen before, so it is not confident. So it is out of distribution. This is something that does not belong to me. So this is very important, specifically for the cancer, and for other kind of disease. But we have experimented with the different malaria and skin cancer images. So the skin cancer is one of the most common type of cancer, and there are around 1 million new cases of cancer only in 2020, and it's growing every other week. So the early diagnostic, including the detection of cancer and its correct classification, has correlated with a high rate of overall survival. So there's a clear pattern and research and quantitative results that if you're able to detect cancer in the early stages, and there are a lot of type of skin cancers, and there are a lot of type of moles, the abnormalities in the skin which are not cancer. So if you're really able to classify it well, then there's a high chance that you will be able to will be able to save it well. Okay. So in also, for example, similar to the other part of world, in Pakistan, in your country, there's fourth leading cancer type of death is cancer. So for example, 6% of all cancers in the male and the 5.36% of all the cancers in the females are of the skin cancer. So here are some examples of skin cancers images. They are taken from dermoscope. So each column shows you one specific type of cancer. So there are 1, 2, 3, 4, 5, 6, 7, 8. So these are the cancer types, and the C is a benign, so it's not a cancer. So other than that, they're all are cancers. So for example, and you see there's a lot of changes, difficulties and differences. For example, in the E, in this type, you can see that these two images, E, first row and second row, they both belong to same cancer type, but they are extremely different. They look extremely different. Okay, and then for example, you have basal cell carcinoma, and it's kind of invisible. In the B, you can see it's kind of it's not that easy to see that is it really cancer or not. Okay, and then you can see in the first type, you can see that there are still the patterns which is not very much clear. Okay, and so you can see that it's very not that easy to find out even for the human eye to whether it's a cancer or not. So main idea here is that, so if you given the image, for example, here the, and you have some machine learning learning algorithm, and it is you extract some kind of AI features, some edges, some corners, some kind of some other stuff from there, and then you plot that. So here in this graph, basically what you are seeing that you see some images and then you plot that. Okay, so here you can see that this is a really a cancer. ID mean in distribution, which means is a cancer, and this is not a cancer image, OOD, and ID sample. This one is again a cancer, and this sample has nothing to do with the skin cancer. This is a tissue image. Okay, but in the feature space, if you see this, these are very close to each other. So the machine learning algorithm is definitely going to fail. So for example, the purpose of machine learning algorithm here is to classify that whether they are close to each other, which is this is here, this is here. So when you have the machine learning algorithm to classify these four images, so it will definitely see this as a cancer, and it will unable to tell you that this image does not belong to me. So, but if you have some kind of data cleaning of the feature clean that we did here on the right, you see this sample and actually now is very far from here, right? So basically, you do some data cleaning and you do some kind of clustering, and then you make the cluster to be compact. So you make them that the similar looking images should come closer to each other, and different looking images should go very, very far from each other. So basically, you do learning on these features which you get from the images, so that you get a better representation. So this is one of the most challenging tasks. So just to reiterate, AI algorithm can tell you well that given if you train it on the 10 type of cancers, it will classify those 10 type of cancer very well. But for example, you have a patient which does not have those 10 type of classes of cancer, it will still classify into the form of that type. So it will not tell you that this type of cancer I have never seen before. So this is the problem of out of distribution, which is very, very important because we want to know when our system is not going to work. So this is something that we have designed and our approach. So given the image of, we have an image which is of the cancer. So then we have another image which is of the cancer. Then we have another image which does not belong to cancer. Okay. And so basically what we want to do is that we take an image which is of the cancer, and then we find the distance from the other cancer images and other non-cancer images. And our ultimate goal is that we want to learn such a features so that images that belong to cancer come close to each other, and images that does not belong to cancer should go far, should be very, when we take the distance between them, they are very large distance. Okay. Then we automatically generate some images which has nothing to do with the cancer, and that we use it as a surrogate, as a replica of out of distribution, that we just randomly take an image and do something on that and then put it here. And we want our system to classify, to tell us that this image does not belong to me. So this is the fake image. The fake image that we just take the patches from the different images and make a new image. Okay. So basically, so given an image, we have a positive image, we have a negative image, and we want to classify it. Okay. Okay. And then we learn representation using machine learning to help us classify. So the purpose of this kind of stuff is that all the images that belong to one class should come closer. That all the images that doesn't belong to one class go to get far away, and also the images that have nothing to do with the cancer should also be classified. So we during the training of the system, we're telling our algorithm to tell us, to help us recognize that this specific image does not belong to me. Okay. So during the training of the system, we are training them to have to tell us that this does not belong to me, so that during the testing, if it happens to see a new image, so it can tell us. Okay. So this is some very brief summary of our skin cancer research, and I would love to. You can go on our webpage, and there's a detailed of each of the experiments and quantitative analysis and the details of the data sets, and you can go and see here. But here I just want to have a brief introduction over that. So similarly, we have done some work on the breast cancer. So the breast cancer rate is highest in Pakistan and highest in Asia. And so the 99% of the breast cancer patients, if diagnosed early, are treatable. So interestingly, most of the cases in Pakistan, most of the women who had breast cancer actually did die. And most of the women in UK who has the breast cancer, they are survived. So the reason is that in the people in Pakistan, due to and also developing countries, the people actually go to see the doctor when they are really sick. So they don't go for the early diagnostic, and so when the doctor is going to see the patient, he is already on the last stage of the cancer. So early diagnostic here is also treatable. So for example, out of the as you can see, every 1 in every 9 women in Pakistan is likely to suffer from the breast cancer in her lifetime, and there are a lot of deaths every year. So, according to the recent research, every woman after 40 years must go to her mammogram scan, and the later can reduce the chances of recovery from 1 to 10%. Okay, so it is very important that we would be having the early diagnostic, and for that we should have the better treatment. Okay, so on the left, I'm going to show you the mammograms, the mammograms of the breast of women, and on the left you see a benign, so which is not the cancers. This is basically calcium ducts, and in the right side you can see a mass. So this is a malignant. So this is a very clear example, but in the most of the cases they are very difficult to see, and they go unattended. So so using this AI, we can able to find out some of the regions where which can be potential areas of cancer. So, for example, this is some of the one of the data set which is available in the for the breast cancer analysis, and they have basically they use the different chemicals, and then they can have the different indications. So basically, for the if you have a tissue, so here are the tissues, and here is some of the region of interest extracted from that tissue. So basically, you can see here is the ER mean estrogen receptor, then progesterone, PR mean progesterone receptor, and then we have gene hypothetical green, and then we have auxiliary lymphocyte node. So these are different kind of status. So which is negative and different kind of indicators, biomarkers, through which we can classify whether this is a cancerous tissue, this part of tissue is cancerous or not. So our research actually focuses on to classify. So given the machine learning, you take those images like this. So you have these kind of patches, then you divide those images into there. So our key observation here was that, so because these are the tissues and then you have the cells, so they have repetitive patterns. So what we did is that we have an image, and then we have the discrete Fourier transform and discrete wavelet transform from that. And then we convert those images into the phase and magnitude spectrums. And then we have to extract features from that. And finally, we have some kind of algorithm to get it classified. So the main crux here is that, so similarly, the image classification, you can do it here at get the tissue, image of the tissue, get those regions, give the machine learning that specific patch, and help us to classify better. Extract different kind of features from that, some edges, some corners, some circles, some repetitive patterns, and help us to classify it. Okay. So so then we again, so this you can have a this work can be, you can look at into our website, the lot of details are available. Then we have some recent work on retinal image enhancement. As I have mentioned at the start, so when you say medical image analysis, you mean enhancement, you mean classification, you mean tumor counting and all this stuff. So we try to work in all these areas. So for example, in the first row, you see the images of the retina. And so these are the areas in the yellow boxes which are not very much clear. So you have any equipment, you bought some equipment from the medical equipment, you take an image, and now image is up to you. Okay. So after the image, you want to improve it. Okay. So we have some techniques, we developed some algorithms which can help improving the pattern. So you can see here is that, so in the yellow box, you see here, so these patterns, it's not very much clear here, but when you see in the down images, they are very much dark patterns. So you can see these arteries very much clear which are already there, but it's not very much clear. So, for example, here you can see the arteries here, but here you can see they're very much clear. Similarly, here and here. So, for example, you can see there's some veins and arteries. I think I don't know whether it's arteries or vein. I think it might be veins, but these veins are much more clear here. And in the bottom row, you can compare side by side the patches. So, left patch shows original image, right patch shows enhanced image. Again, left patch shows original image, which is enhanced image, original, enhanced, original, enhanced. So you can see there that even you get an image from very expensive, there's from some equipment that you have, you can do a post process and improve the quality of the image and to have a better visualization and a better diagnostic. So here is some details of the medical, some of the algorithms, but we don't need to go into details. And here are some of the visualizations that we try to automatically generate these images. So given the image, which are there, we use some kind of techniques to add noise and then improve the quality. So here are some of the enhanced images. Okay, so then the medical imaging have advantages in cancer in the MRI. So for example, you can see here is that in the left. In the left, you can see there's a right helium, the left helium, and these are the normal structure that we really want to observe here. So, but here in the left, you can see that here's a decreased lungs volume, and which is the aggregate should be like something like this in the right, but the left you can see that the lungs volume is decreased, so which is an indication of the volume. Then, for example, the original structure of the lungs should be like right, but you see some abnormal patterns here, and then which means you see that it is an issue creating. Similarly, you see these small kind of structures here which can create a problem. So this small dot here in the left is actually a lung cancer. So and it can be a little bit. It may not be that much obvious. Okay. So and it can easily be missed. Okay. And so it's for the AI technology we want you to make it more enhanced and more better. Okay. So this kind of stuff. So here I'm showing you a cancer image in lungs MRI, and you see that there's a lot of patterns here, here, and here. So in the Harvard Medical School, an interesting research. What they did is that they put kind of abnormal pattern in the image and gave it to the doctor and asked them what you see anomaly. And the majority of the doctor was unable to see some hidden pattern like gorilla here. So you can see here they have this is gorilla, which has nothing to do with their MRI. So most of the doctors was unable to. 83% of radiologists didn't see this gorilla. So they have this here, but most of the doctors was unable to see it. So the idea was there. If the doctors are missing, are looking at so much information, why they are unable to look at this abnormal pattern? And the reason is that the conclusion was that they were focusing on specific patterns, specific regions which are most probably belong to the cancer, and they actually missed those unobvious regions which may contain some abnormal patterns. Okay. So similarly, medical diagnostic has applications in surgery. So the surgery, what do you mean surgery? Surgery treats disease and injuries by removal, repair, and adjustment of organs. So the patient needs surgery due to the following reasons. For example, it needs diagnostic and remove or repair disease tissues or organs, and reposition the structure, redirect blood vessels, transplant tissue and whole organs. So, according to the Wikipedia, we have 4.2 million people that die within the 30 days of surgery per year. So because it's which is very alarming. So obviously it depends on the people medical conditions. It actually is highly dependent on the person or the surgeons performing the surgery, because one of the major cause of death is a blood loss, because a surgeon performs surgery need a space to move his hands. So due to the bigger cuts, so it may increase the blood, and then which can be which may be problematic. So that's why here comes the EA solutions, which basically help us to remove the help us to get it the robotic surgery using the EA camera. So and that's why basically here the A is used. Secondly, the evaluating and scoring the surgery is a very time consuming and a personal task. So, for example, heart surgery, it takes around 8 hours to perform the operation. Then you need another 8 hours of the senior doctor to see whether this surgery was performed well or not. So that's why we need AI-based solutions to help us to find out the reasons. Okay. So here is example. So to train the train the medical AI algorithm, we need some data, but it's not that easy to get that data, and and that's why we are here. We need some other kind of data to do it better performance. Okay, so basically, for example, if you look into these videos, you have these kind of surgeries, you can have these kind of videos, and then you have so basically you train your system over the different kind of night tracking, over the different kind of data on the VR, and so that it can help better performing on the real world video. Okay, so these kind of data will be used for the training of the system, which is ultimately used for the surgery. Okay, so this is one of the beautiful picture released by Siemens last couple of years ago. This is of the cell, and you can see there's a lot of things going on. They enhance the visualization. So this complete my general introductions of the medical imaging analysis. Of the different applications. So we will be having 5 minutes break, and you can have any questions. And then after break, we'll be going into the details of our work on cancer and the malaria. So we will be having a 5 minutes break. Okay, thank you.
Hello.
Okay. Thanks, Dr. Vakas, for a very nice lecture. So for the students, I would like to
If you have any question, please feel free to ask.
Okay, just like
So there's a lot of echo here.
Okay. So you see, I would like to have, like, if you have some questions, please feel free to ask. Pardon.
There is one question online.
Sure. So what's the question?
You can check on the web, on the online.
Okay. Okay, so thanks. That's an interesting question. So I think I never worked on the nano robots, but I think there's a definitely lots of use, because thing is that the medical imaging provide you the very precise measurements, and also uh, it can provide you the 3D registration. 3D registration means that you can map the image to the real world application. So, for example, in the image, these just the two things are, for example, two tumor are apart. I mean, by two mouse click are 10 pixels, but in the real world they are apart by 20 nanometers, for example, millimeters. So basically, are micrometers. So basically, so medical image provide you the accurate information, so you can use that to help robot to have accurate operations or the surgeries or the tumor removes. Perhaps that actually this medical image stuff is used by different hospitals in the US. So to one of my friend actually working, he did medical physics. He did PhD in medical physics. So they are using these images to have the precise laser treatment for the cancer. So yeah, so it will be very useful there. Any other question, please?
Please proceed.
Okay, thank you. Okay, so let me first jump to the I'm going to skip something, and then so that and then coming back to the to the Hadaraf again. So here's the thing. So let's see. Okay, so what I'm going to do now is I'm going to provide the detailed introduction of our work in the malaria and the cancer and peripheral blood slides. So, we are basically going to use object detection for the malaria. So, as some of my might know that there are annually 226 million cases of malaria, and there are 400, around more than 400,000 people died every year, and 67% of them are the children. So malaria is also named as a disease of poor. So mainly the resource deficient tropical and subtropical regions, we have the issue of these are the regions which are mostly affected, and these are the regions where basically we have we need the treatment. So, to your knowledge, there are around more than 3,000 species of malaria, and so basically, if you see here that so there's a lot of regions in Africa actually, so that you have where the people died of the malaria, and there are a lot of regions. So, for example, here you can see in the map. So these are the regions, the red regions, which means the malaria occurs throughout. Okay, so in the developing countries, usually they don't have the malaria because they have the better sanitation conditions, and they have the better spray and all this stuff. But the several regions, including Africa, because of the jungles and because of the trees and because of the poor sanitation conditions, and in developing world, so there are a lot of issues to the malaria. So it's a very important problem. So we have usually, to your interest, we have around 3,000 species of mosquitoes, and out of them, that 400 species of Anopheles mosquito, only 60% carry plasmodium, and the parasite that carries malaria. So it's not every mosquito is a dangerous from the perspective of malaria. Only a few of them carry plasmodium. Okay, so according to the World Health Organization, only in 2018, 228 million people have infected with malaria, and 400,000 people died globally due to malaria. So to do this, to diagnose malaria, usually what we do is that we get an blood and put it on the slide, and then we spread the blood over the slide, and then we put some gymnastine to see to analyze that blood slide. Okay, so for example, here are the images that we took from ourselves in our lab. So you can see. So in the malaria, basically, red blood cells actually get infected. So what happened is that your red blood cells get infected, and these all the time they get multiplied, and then you are going to lose your blood. So, and that's where the death happens. So early diagnostics is very important. Otherwise, it is a multiplicative process, and if the person is not properly treated for 1 or 2 weeks, so he's most probably going to die. So and also different malaria types needs different kind of medicines. So if the person is not treated well, so he might get wrong medicines which will not have any specific effect, and ultimately it's a disaster. So here are some pictures of our lab where our students are working in the laboratory, and they are working in a close with some medical practitioners to collect the data and analyze the data. We have a microscope. We put some camera, and for example, here we put some camera and also mobile phone over the microscope to see how it looks like. So, and we then collect the data. Okay. So here is what you see when you take the image on the 100x microscope, and the images are, the cells are very, very small, and then you have the 40x, which is 400 times bigger. Then you see the cells is bigger, comparatively better, and then you have the 1000x, which means 1000 better, and then you have the detailed picture. So the gold standard for the malaria is 1000x, 1000 times increase the size, so you can see the internal details. So here are some examples of the images that we took ourselves in our lab. In the first row, you see healthy images. So these are the very healthy white blood like red blood cells. And the second row, you see there's a ring stage, and within the cell, you can see the appearance of a ring, and which is abnormal. Then in the third stage, you see trophocyte, and this you have a couple of dots in the within the cell, which again represent anomaly. And then we have a Schizon stage, where we have lot of dots here. And so after the Schizon state, actually the cell burst, and these small dot actually go inside the cell and make it them infected. So this cycle from healthy to ring to trophocyte and Schizon is actually of 24 hours. So that's why when you have a cyclic fever of 20 after 24 hours. And the last part is a gametocyte, which you see has a different structure. So it is very easy. It's very useful to detect these different types of stages of the malaria, to actually know how much infected the person is. So here are some examples of the different white blood cells which are infected with the malaria, and you see it's not that easy to diagnose it, because in the fourth column you see there's a lot of structures appearing there, but they are not malaria because they are just dust particles. Okay, and then in the middle you see the ring stage, but in the third column you see the ring stage, which is again not very obvious. And then the Schizon, and then the trophocyte and ring stage. Okay, so what we did is that we given an image of the patient, we do the segmentation, which means that we get a bounding box across each of the cell, and then we divide this. We, after getting each cell, we basically passed it through the convolutional neural network, and to decide whether this is infected cell or not. So if it is healthy cell, then we don't care, we don't bother about that. And if it is infected, then we give it to the another neural network to classify whether it is a ring stage, is a trophocyte, is a Schizon, is a gametocyte, or a healthy cell. So what we did is that we work with a local hospital, and then we make a mobile app where you can actually load an image into the mobile, and then you can actually see with the doctor. You can press the count cell, and it will count the number of cells of the malaria, and then it will also, you can press check malaria. It will also count, and it will show whether how many malaria cells it have seen. So this is something that we have worked with a local hospital. We gave them this app, and they were very useful for them. And also they use it for the teaching purposes, for the teaching the young doctors that okay, the different stages of the malaria look like this and that and all this stuff. So we not only show the cells, we also show which one is the malaria and why they classify it in malaria. Then we also use it for the to make because in the microscope you see only a small portion of the big picture actually. So what we did is that we stitch in the image processing, we stitch different parts of images, and then we show it in a very large image. So you don't have to. These are the small images that you see, and then we do the image stitching, and then you see the whole image. So the whole slide image, you can see how it looks like, and it can make the counting and the classification of the malaria very easy. So again, the problem is that we started with in developing countries, people observe poor health facilities. What we believe is due to the three main reasons. One is that expensive medical instruments are not available. So they are very, very expensive because the area is already poor and they cannot afford to have a very expensive medical instruments. Then the doctors are already lacking. So they don't have sufficient time to analyze the outcome of these instruments. So there's only few doctors which are very, very good, but they are very, very busy. So in remote areas, to get the appointment for the very good doctor sometimes takes several months. So, and also the data itself is not digitized. So you cannot verify what the person have seen. So for example, I'm a junior doctor, I look at the blood slide and then I make a judgment that this person has stage 3 cancer, blood cancer, for example. How I make that judgment is not clear to my senior doctor. So the data is not digitized. So, but the problem is that there are some methods available for the malaria, but they do not affect the core limitation of the malaria. First, the malaria, since happens in the low resource constraints area, so we need to detect on low cost microscope. So, and we need to detect on the low magnifications to make it more useful. Okay, so basically the main idea is that we say that malaria is happening in the poor areas, but if we really need a very, very expensive microscope, which is one of the basic equipment, then we are out. This is chicken and egg problem. So you don't have the money for the sanitation purpose. You don't have the medicine for the money for medicine. But again, to diagnose it, you need a very, very expensive instrument. So this is one of the motivation that we work for. So for example, in the left, I'm showing a popular Olympus CX23 microscope, which usually cost more than $3,000. And then on the right side, I show a cheap microscope, which is XSN107BN, which is around $180. But the issue is that the left microscope has very good optics and very clear images. If you take the picture of those images, the right, the microscope is not of that good quality, and you can see the smaller area, and it's not good for the analysis purpose. And the doctors itself who are trained, they are not that comfortable on that. So our objective was to have detect malaria on the low-cost microscopes and detect malaria on the lower magnifications. And this was a paper which was published in one of the top venue in computer vision a couple of 1 or 2 years back. So this is the image you see. So the left we show the image which are taken by high quality microscope, and on the right we show the image which is taken by low cost microscope. And in the middle we shows the different cells, and the color correspond to the same cell type. So the images are taken at 100 time resolutions, which is 100x or 1000x, you can see. So the left side, you basically, the low quality microscope usually has smaller field of view, and the image is blurred, and also the less precise knobs. So, and the left, you see the high quality microscope image, which is more clear and more precise and more easy to look for the diagnostic purposes. Okay. So our idea is that we want to do the classification on the low quality microscope. But the problem here is one of the challenges that the doctor don't trust low quality microscope. So they want us to do the analysis and all this stuff on the. I mean, they're not confident, and we agree with them because the patterns are not that much clear. So what we did that we take two microscopes and we asked the doctor to look at the high quality microscope, help us annotate those images, and given the image, tell us which cell belong to which type, and then we will do our matching ourselves and find exactly the same cell on the low quality microscope. So here are the images. For example, the left row you see three images which are taken from the different patches, and basically this shows the different so exactly the same patch, but they are at the different resolution: 1000x, 40x, 400x, and 100x. Okay, on the right side you see the same images, exactly the same patch, exactly the same cell, but with the price of $180 microscope. So you see that the quality of the image is very poor and it's not that much obvious to see. But we really want to get the analysis and annotation on that. So this is the comparative analysis of the patch and the different axes. So on the left you see a patch at 100x, then we see the exact patch at 400x, then we see the exact patch at 100x, 1000x. Okay, so the different images looks very different. I mean, the quality of the images changes as you increase the scale of the microscope. So what we did is that we want to collect exactly the same image at the different microscopes. So what we did is that we have some small technique. We had a microscope and then we have two extra cameras. And the cameras were focusing on the X coordinate of the microscope and the Y coordinate of the microscope stage. And whenever doctors see the cell, we take the pictures of these coordinates. And then that help us to put the slide on any other microscope, and we go to exactly the same scale and we find exactly the same cell. And initially it was very challenging, but later on we have a very seamless process to do this. So given the microscope, we have images. So doctor help us to find a patch which he or she believes has a malaria. Then we, given that patch, we actually map those to the microscope using computer vision techniques, and then we actually track those patch across the different fields. So we know where this patch has gone. And finally, we use the image processing to track those patch across the different locations. So in the bottom left, we show the three patches which are extracted at different resolutions. So basically, for each image that we repeat this process. So it took us around maybe 1 year to 6 months to 1 year to collect this data set. So we believe this is one of the largest and one of its own kind data set, where we have the multiple magnifications and multiple microscopes. And we have world's largest collection of malarial cells, where you can see each cell in the different microscopes, and also we have the largest collection of the images itself. And then what we did is that we use different kind of methods which are available to detect objects, and we trained it over the malaria, and then we tested it over the different resolutions. So we have the different training 1000x, 100x, and 40x images, and we tested on them. Okay. And then we have some kind of machine learning techniques to improve that results. And these are some of the results where I can see, we can see that there's a huge improvement of our results as compared to the state of the art. Okay. And these are some of the results which are automatically generated by our method. So given an image, it is able to predict the different type of malaria automatically, and these different curves show the different type of malaria. So we have very interesting results over by using the low quality and high quality microscopes. So what we did is that we extended the same thing for the blood cancer. So, and for example, and the reason is that in 2020 alone, more than 1.2 million new cases of blood cancer were diagnosed in the world, and more than 7.7 million died. So again, the early diagnostics is very, very important. So one of the most important steps for the diagnostic purpose is to analyze blood and bone marrow slides of patients through the microscope. Okay, but again, microscopic analysis is a taxing process requiring expensive microscopes and trained experts. So, but we repeat the same procedure that we did for the malaria, for the cancer stuff. So this is our setup. We have one microscope, which is a high cost and around $3,000 and $6,000 with a camera and microscope, and we have another microscope which is around $1,000 microscope. Okay. So and we want to relate to get the data from that. So in the above you see we have high quality microscope. We get the images, and then we capture the different white blood cells. So in the cancer, our main focus is white blood cells. In the malaria, our main focus is red blood cells, because in the malaria actually attack white blood cells, and blood cancer attacks the red blood cells. Okay. So here is the some details of our data set. We have 48 patients, and then we have the different types of white blood cells like myeloblast, lymphoblast, neutrophil, monoblast, atypical lymphocyte, promonocyte, lymphocyte, myelocyte, monocyte, and basophil, and all this stuff. So we have all these stuff at the different these cells. So here is an example of white blood cells, and you can, to us, to the non-medical doctor, it is all these are the same, look same. But actually, the first one is monoblast, second one is monocyte, third one is myelocyte, and fourth one is lymphoblast. And actually, they have different kind of attributes. They have the nuclear chromatin. The first one is open, second one is coarse, the third one is coarse, and then it is open. And so they have different kind of details of nuclear shape, nucleolus, cytoplasm, cytoplasmic basophilia, and just cytoplasmic nucleus. So it's very, very different from each cells. So here are the details of the data. So what we did is that we have multiple microscopes, but we had multiple cameras, and then we used multiple resolutions. So the purpose is using the multiple microscopes and multiple cameras is to collect data at different locations to collect for the different microscopes, so that our method is, when it's trained, it works robustly across different microscopes. So what we did is that, given the peripheral slide cells, we basically get the images, and then we train a neural network to classify different cells. So in the bottom you can see our method is able to classify different white blood cells into neutrophils, myeloblast, and monocyte, and so on and so forth. But the one issue is that you give a to take an image, you apply ML algorithm, and it will give you the results, that the classification results. But why should the doctor trust it? Then we ask the doctor why, but you look into these cells when you classify it. So they tell us different attributes. So then we say to have confidence from the doctor, we basically have another network which actually predict attributes. So basically, what we did is that we, in addition to just prediction objects, like different kinds of cells, we also try to predict the different kind of attributes. Attributes mean like what's the nucleus look like, whether it's open, and what other attributes are. So once we have the attributes, we can able to, for example, here is that. So for example, we have these predictions. For example, we have the cells myeloblast, myelocyte. Then we have the none, which means it's nothing. It's nothing to do with the white blood cells. Then we have metromocyte and neutrophils. So we have all this stuff. Okay. So we have then these attributes because we have trained the model for each cells. We know whether it's small to medium size, whether it's scanty, whether it's conspicuous, whether it's dispersed, whether high, moderate, something. So we have the keywords. Okay. So using that keywords, we can generate a report. Okay. So we can give it an image. We can generate human interpretable report that these blast cells are small to medium size with scanty amount of cytoplasm, high NC ratio, moderately condensed to disperse chromatin nuclei, inconspicuous nuclei, and inconspicuous nuclei. These cells contain locus. Okay, so we have been able to generate this human interpretable text, and we showed it to the doctor. Obviously, we have a lot of discussion with the doctors, and we showed the doctor, and they were really, they think that is a useful stuff for them. Okay, so basically, what we discussed, we submit this this research work is still under process and under submission. So we also extend the same thing so to the few short learning, which means that the machine learning algorithm usually need lots of examples. So which is very difficult, specifically in the different diseases cases. So we have what we did is that we trained the model on the few examples, and then we want to classify those. So we actually have some similar kind of stuff. We have during the training we have very few examples, and then we use those to train the model. So I will not go into details. If you have some questions, I would love to answer. So these are some of the other details. So the main idea here is that given the cells, we want to decrease the similarity between the similar kind of images and the dissimilarity between the different kind of images. So you want to extract some features like edges, corners, and color, and you know that the images are the cell which belong to same class. For example, the neutrophil, they should have the same color kind of edges, same kind of colors, and the images which just belong to a similar class, they should go to the different classes. Okay. So this concludes my today's lecture. So what I did is that I did a brief introduction of our work in medical imaging. I also talk about a little bit about general object detection, but I couldn't have time for that, but I can also go into details for that. I actually skip those portions, and then I will give a detailed introduction of the work on malaria and cancer. So yeah, please free to have any question if you want.
Thanks. I was about to say this. Very nice. So,
Any question, please?
thanks, Dr. Vakas, for such a nice lecture and for your time. So I think it will be slightly difficult to take questions and give it to him. So what I would propose, if you have some question, you can ask from me, or you write on a Zoom if you have joined online, so that he can answer. Okay. I think most of the people, they have joined online, so you just type in the message window. Okay. And if still later on, if you have some question, you can let me know. And he has also shared his email ID. If you haven't noticed, you can ask from me. So
Yes, you're absolutely right. So the model definitely is affected by spatial resolution and contrast resolution. So contrast resolution, and that's the issue. So what we did is that and that's why we have the multiple microscopes and the multiple resolutions. So since the algorithm that we have is actually have seen during the training different microscope and different data, so it performs much better as compared to whether it is just trained on one kind of system. So when you train your A model on the only one type of images on one type of resolution, but when you test it on some little, you just change the resolution a little bit, it will the performance will degrade drastically. However, during the training, if you have given different kind of images, different kind of resolutions, different kind of quality of the images, what we have done here, that we have the different microscopes, different resolutions, so the performance degradation is not that bad.
Doctor, please repeat also the question that the people in person here can understand.
What?
When you receive the question, please read.
Yeah, I answered that question. Okay, so the question is, what is the success rate of the model? So is the work affected by spatial resolution and contrast resolution of imaging system? So the answer is yes, it is affected by the spatial resolution and contrast resolution. So the idea here is that whenever you train a system, EA system, machine learning, and deep learning method, it will be specific to that specific spatial resolution and contrast resolution. So to make it work better, generalized, so what our idea is that we use the images from the different microscope and different different kind of microscope and different images, so that it learns during the training. It have seen all these kind of variations, so it learns well. So the second question is, what kind of camera do you use for cancer detection? We use just mobile camera. We're using just mobile camera. We have this microscope, then we put the mobile camera over the eyepiece and just use that. So, for example, yeah, this is interesting. Let me see. I'm going to write it here. Honor 9 Lite. And so we use this Honor 9 Lite mobile just for no reason, because we find it cheap, but you can use any mobile.
Dr. Vakas, thanks.
So the question is, where do you get your samples? I.e., do you culture the cancer cells, or do you use humans or animal models? Actually, we got these cancers blood cells data from the local laboratory in our near in our city. So because we currently we are the computer scientists, we are not the doctor, so we get their help. So they have done. They basically what they did is that they had a blood cells and then they cultured these blood cells themselves. And what we got is that we got peripheral blood slides, and we took the image from there.
Okay, so with this, I think we close this lecture and thanks again to Dr. Abbas. Thank you. Okay, with this, we would like to invite next speaker who is physically present here, Dr. Dixon. So, who did his bachelor's and master's in Kenyatta University. His PhD is in optics from Huazhong University of Science and Technology in China. He specialized in nano optics and currently involved in applications of nano optics in biomedical area. So let's welcome Dr. Dixon.
So good afternoon. So I'll be speaking about the potential of optical biosensors in bridging the diagnostic gap in developing countries. So basically, this is how I've structured my presentation. So, and because the optical biosensors involve quite a range of devices, I've narrowed down to two. One of them is the fiber optic biosensor, and the other one is the calorimetric biosensors. And then finally, I'll tell you some of the research activities that we are engaged here at NEOL. Yeah, move. So I will start by a very small introduction about the burden of the disease in the world. And we quantify it using the disability-adjusted life years, which basically is a combination of the premature mortality and years lived in disability. And clearly you can see that the biggest burden is more on the developing countries. So if I try to look at the relationship of the disability-adjusted life years in relation to the gross national income, apparently it is very clear that, again, there is a very direct correlation between the gross national income, of course, which translates to the earnings per person. There is a direct correlation because you can see the countries with, minimal gross national income actually have a very high disability, just 10 years. So basically why I'm showing this is because then it tells you that clearly there is need for us to develop alternative diagnostic technologies that are cheap enough to ensure that the people living in these countries also have access to proper diagnostic and are enough. And in this case, that ensures that probably the treatment can also start sufficiently at an early stage. So then I'll introduce the optical biosensors. In general, first I start by defining what a biosensor is. So a biosensor is an analytic device incorporating a biological sensing element. And they are used for a range of applications ranging from water monitoring. We can use them for disease diagnostics, environmental monitoring, soil quality, food quality monitoring, pathogen discovery, and drug discovery. So, and specifically, this range of devices are usually very direct and real-time, and they produce results with very high specificity, sensitivity, and to some extent they are cost-effective to be afforded by the developing countries. Is this thing working? So basically, this here are the basic components of the biosensor. We have the sample of interest. Then we have the biological elements or the bioanalyte that we are looking for. In this case, it could be an antibody. It could be aptamers or enzymes. Then the transducing process. It could be electrochemical, optical, mass, or magnetic. After that, probably you need to do a little bit of signal processing, which involves bit of amplification and, if need be, to filter a little bit of the noise. So biosensors are classified, in this, and our focus today is the optical biosensors. So there are quite a number, and as I've said today, my interest will only be two. That is the optical wave fiber biosensors and the calorimetric biosensors, which rely on the localized surface plasmon resonance. So basically, optical biosensors exploit the interaction of optical field with the bio-recognition element, and they are divided into two. One is the label-free, where the target material that we are analyzing directly interacts with the light energy, and then we can extract the required information through a transduction process. Then we have labeled, where we use dyes or nanomaterials. For example, we could use fluorescence to do the labeling and be able to quantify our particles of interest. So I'll start with now the fiber optic biosensors. In principle, this diagram here, part A, shows exactly how we can use a fiber optic as a biosensor. And we leverage on the fact that when the incident beam is internally reflected, the intensity does not go to zero instantly. It takes some time. And also the fact that part of this beam can be able to penetrate the refracting material and travel some distance which can be defined by a portion of the wavelength. So the other very important thing to note here is the fact that we can have some wave penetrating the refracting surface. Then we could be able to put our material of interest, which is a biological element here. And because we know most of them are absorbed, then the refracted beam here is going to be a little bit attenuated. So, so in this configuration, of course, beyond the fact that you know we have this beam traveling a certain portion of the wavelength, other things you can do to influence the penetration depth is doing what we call index matching, ensuring that the wavelength is suitable enough for the element that you are testing and also the angle of incidence. So basically, there are two very key mechanisms or ways in which we can do the sensing. One is from the fact that once the evanescent wave propagates at the refracting surface, it's absorbed by the material of interest. And what that means is that then if we actually record the refracted intensity before introducing our bioanalyte, and then the intensity after introducing this, then the difference here is going to define the absorbance, and from the absorbance we could extract parameters like the Mora extinction ratio, and also the concentration of the solution, that is if we, or the analyte, that is if we vary the concentration. So that is one way. The other one is what we call the total internal reflection of fluorescence, and Roberto has already explained this diagram here. So our mechanism of interest is fluorescence, which occurs at here, nanoscale, and photofluorescence. These are basically, you know, phenomena that we normally group as photoluminescence. And from here, we can extract parameters like the Mora extinction coefficient, the quantum yield, and the fluorescence lifetime. So basically, in this configuration, what you do is the fluorescing signal is sent back to the fiber and propagates to the detector. So then I will probably show you what people are doing now in terms of this type of biosensing. So basically, you could incorporate a spectrometer to leverage on absorption, fluorescence, or fluorescence. Basically, these two are photoluminescence, Raman, and surface plasmon resonance. And a very interesting paper that I saw recently is this, where they are using the fiber optics, but then they use a class of this transitional metal dechloridized materials to enhance the sensitivity of the sensing surface. So by using this, actually they showed that the sensitivity enhances by, I cannot remember very well the factor. The other trends in this area, I think, is the use of plasmonics, nanomaterials, or basically plasmonic materials. And another paper that I found that is very interesting is this that was published in Biomedical Optical Express, where they are doing all label-free optical biosensing. Okay, so on the calorimetric biosensors, from a physics point of view, I think it's very important for us to first of all understand the concept of localized surface plasmon resonance. And for us to be able to clearly understand this concept, we start with the Mills theory, which solves the Maxwell equation for absorption and scattering of the electromagnetic wave of spherical particles. So basically, because the nanoparticles are much, much smaller than the wavelength of the light that we are using to probe, then we use the dipole approximation to obtain the absorption. And basically, the extinction coefficient in a quasi-static regime is given by this. Where the parameters are as defined here, the surrounding medium is always assumed to be independent of the frequency. And then to ensure the resonance conditions, equation 4, the conditions of equation 4 must be met. And to meet this, actually, we require that the imaginary dielectric function should be very small, relatively in comparison to the real part. So in practice, this is what happens on the size effects of the plasmonic absorption of maybe this is a classical example of metal nanoparticles, and you can see basically what happens is that as you increase the size, even the absorption shifts, or is basically red shifted. Now, how exactly this type of theory helps us in developing calorimetric biosensors is the fact that when you introduce a material inside the solution of, for example, gold nanoparticles, they aggregate and they shift to longer wavelengths. So basically, you can be able to visualize exactly this shift, the red shifting. So basically, these are the steps that are involved in the fabrication of gold, and I'm picking gold nanoparticles here because I need to narrow the discussion to a specific biosensor for purposes of ensuring that we clearly understand basically what is happening. So the first step is you have to synthesize the gold nanoparticles. Then from there, you have to functionalize with the bioreceptor. In this case, it could be an antibody, an aptamer. And then, of course, from there, the step now, the last step is the biosensing. There are quite a number of, because this is actually the most demanding step, that is the functionalization. There are quite a number of procedures that we can use to do that. Most of them are chemical, but the one that is really of interest is what we call the photochemical immobilization techniques, developed by Professor Verota at the University of Naples. Because actually for this type of functionalization, you do UV activation. The UV activation opens up the required parts for tagging with the bio receptor. Actually, a study was done recently, I think last year, to compare these methods of functionalization. And the conclusion was that the UV activation is actually more efficient in terms of activating or making the functionalization process. But beyond this, this process happens very fast. Last summer, I happened to visit his lab, and typically the functionalization process or the activation process takes roughly 30 seconds. The chemical methods, maybe they will take hours to do that. Beyond that, as you can see from the diagram here, the antibodies orientation is not random. It's actually very well oriented. So the other thing about the photochemical immobilization is the fact that you get better conjugates with higher yield, and the process is highly reproducible. So now I will explain what now people are doing in terms of the calorimetric biosensors. One of them is using of what we call optical leaders. So one of the typical calorimetric sensor is this device. Not all of them, of course, are based on the gold nanoparticle, but some are. And I think most of us must have had an experience with this kind of test, right? Yeah? So basically, the problem with this kind of test is that it cannot give us, a quantitative diagnostics, because the healthcare person, or if it's you, you just look at the line and you give an interpretation. It is either positive or negative. But then the level of the infection cannot be really known, and that brings a problem, because then how is the healthcare practitioner supposed to know the right amount of dosage of drugs that he is supposed to administer to you? In some cases, there is quite a number of publications that have shown that there has been misinterpretation of the lines, especially where the health practitioner has issues with the eyes. So I mean, the observation is really subjective. So what people are doing is now to try and develop optical readers to actually quantify this. Beyond the quantification, the fact that we can be able to convert this information digitally means that we can facilitate now real-time reporting. And in cases where there is an outbreak, then the authorities are able to map the areas very fast. They're able to map the areas very fast. So basically, when even by taking an image by your mobile phone and then do a cross-section profile, you get something like this. So this is the control. Probably this defines the number of, the level of, the infection, which we cannot be able to actually visually interpret. So that is one. In this domain, we have also done some work with COVID samples. In fact, we recently received a provisional patent for this. And basically what we are doing is that we were using different, dilutions of COVID. By the way, this grant was funded by the National Research Fund of Kenya. So basically we are using different dilutions, then do a surface profile of this. But basically the novelty of this was that we tried to use very low cost, optics. So basically our optical kit that is supposed to do this, eventually we hope that it's going to cost less than $2. So basically this is the flow of exactly what we have been doing or are doing, because we have not yet finalized the process. So we have the lateral flow, then we have two modes. One of them is the reflection mode and the transmission mode. To vary the effects, sometimes we use specific color LEDs and also white light. The information we get, we transfer it to the computer, and basically, this is a process that we were following. So we would load the lateral flow assay on our kit, capture that image. Of course, we would crop our region of interest. Then load the sample, which were the COVID samples, followed by, again, another capturing of the image. Then we subtract the difference between the first, which in that case involved the lateral flow assay without the sample, and the image after mounting the sample. So this is just a result of two different directions, and you can clearly see that we can be able to distinguish between two different directions. By the way, the other thing we noted is that sometimes the infection level is too low, and the medical practitioner cannot be able to visually inspect that and show that either you are, you positively have the disease. But by using this method, we could be able to extract the information about the infection level. So that is the work we are doing in terms of the optical readers. I think we are not the only one who are doing this. There are quite a number of people who are doing this work. The other way of doing, improving the biosensors is using additional biosensors. And these two papers are basically the two that I could actually be able to identify that, have done some very interesting work. The first one is published by the, Professor Rafael, and basically what they are doing is to try and have different transducers. Like, for example, here, they used the localized surface plasmon dissonance, that is the color change, but also they mounted the aftermath to improve to ensure that the detection is very specific. But on top of the aftermath, they mounted the fluorescing attacks. So this way, what was happening is while they could get the calorimetric information, but on top of that, when they put the samples in fluorimeter, they could also extract the information about the fluorescence. So basically, what this study did is that they found out that they could improve the limit of detection by, they could lower the limit of detection by almost, I think, 10 times. They went to pico level. They went to pico level. The other interesting study is still related to the same, but in this study, what they were doing, beyond using both the plasmonic and the fluorescence, they also developed a low-cost fluorimeter kit for this analysis. So, and the future is, I think, because these devices, the lateral flow assays are becoming cheaper and cheaper every day and more accessible, what I anticipate or what I see is the fact that the people can walk over the counter, buy this type of biosensors, do their own diagnostics at home, but for verification, if it turns out positive, or even if it's negative and you still feel unwell, you could still take it to the hospital for fluorescence analysis to actually confirm the level of infection. So this way, we ensure that by the time the doctor is prescribing the medication, he is very sure of the infection level, and beyond the infection level, that he can be able to actually quantitatively get what the infection is. Okay, so then I'll tell you what we are doing at Multimedia. So I have two students who are master students who are working on this concept of magneto-optical malaria diagnostics. So I will not talk about this diagram because the previous presenters already explained this. So we go to the next slide. Next. So basically, these are the conventional methods of malaria diagnostics. And the key here is the testing time and the limit of detection. So for example, light microscopy, it takes roughly 15 to 60 minutes on average. And the limit of detection is approximately 5 to 20. Well, this is the gold standard. It's a gold standard. And you can see, actually, in terms of the testing time, the device is very limited because suppose, on average, you have one technician in hospital. So if they are taking an average of 30 minutes, so the maximum they can do is maybe, assuming they work the whole 12 hours, is 60 patients. And probably we have more patients that need the diagnosis. So we also have PCR. PCR is quite sensitive, but then the equipment itself is very expensive. The limit of detection is good. Then we have the lateral flow assay, what we call the RDTs. They take roughly 15 to 30 minutes. But now the problem is the limit of detection is not very good. They miss quite a lot of infections. Well, the concept of optical leaders could be used to improve the specificity, but then they cannot lower the limit of detection. So then we have what we call magneto-optical process, and this emanates from the fact that when the mosquito bites you, the part of the cell, the red blood cell that they consume, they are very much interested with the hemoglobin. Now, it happens that the only bait that is useful to the mosquito is the globin. The heme is very poisonous to the mosquito. So what the mosquito does is that it converts this to a crystal, And this crystal has very interesting properties in terms of the physics because they have what we call magnetic anisotropy and optical decroissing. Now, some studies, not some studies, quite a number of studies that have shown that actually the concentration of hemozoin is directly proportional to the level of infection and the different stages of malaria infection. So, and we could use it as a biomarker for identifying and quantifying malaria infection. So basically what we are doing here is to try and use cheap optics, of course with the interest of making sure that the end product is as affordable as much as it is practically possible. The other challenge with this type of devices, the ones that have been proposed, is the fact that they have challenges generating a uniform magnetic field. So we are also trying to see how we can try and generate a very uniform magnetic field. Our feeling is if we could be able to do this, then we could be able to highly enhance the sensitivity of this type of biosensor. Yeah, so that's the end of my presentation. I welcome questions and comments. Thank you.
Thank you so much, Doc, for the presentation. I have a question. In our lab, Prof. Malik's lab, we are dealing with localized surface plasmon resonance. And the challenge is always how to integrate silver nanoparticles with your analyte, because the configuration is always very difficult. If you shine your laser to the mixture, the analyte and the nanoparticles, at one point you may get an enhanced signal, but another point you will not get. So the configuration is always a challenge. What can you advise?
So if I try to, because I have not understood your question very well. So is this after functionalization? That is, already you have, conjugated the nanoparticles, for example, the silver nanoparticles with the
Yeah, after you have synthesized the silver nanoparticles, you mix with your analyte. So the challenge is the orientation, because all these are fluids and they need to mix. So after mixing, if you interact the analyte and the nanoparticles with the laser, the configuration is always a challenge, because sometimes you may not get the enhancement when you're using Raman spectroscopy.
So what I know is that your process of functionalization, because it's a chemical method, so it's a physical, where you just add. So I'm not sure which mechanism you're using there, because if, for example, it's the covariant bonding, then they are very unstable. And probably it could explain why sometimes you get a very nice signal and other times you don't. So, and primarily that is the reason as to why when I was making the presentation, and I specifically highlighted this photochemical immobilization, because this method is highly reproducible. You can just take your nanoparticles, especially metallic nanoparticles, whether it's silver or gold, irradiate them, irradiate the antibodies or the analyte a little bit, and then just add. So it's highly reproducible, unlike the other methods where you really need a lot of art to do the functionalization process. So maybe part of the reason as to why you are not getting a very consistent signal could be the fact that your yield is not very good enough. Yeah.
Hi, Dixon. Great talk. I'm very much interested in this type of work. I don't know if I had already mentioned this. In our university, we have a program that's called Frugal Biomedical Innovation. And our goal is to develop not lower quality, but similar quality devices for low resource settings. And this would likely very well fit into the type of program. And we have partners in Africa and in northern Canada where access to high quality healthcare is a challenge. So I'll be very much interested in connecting you with my colleague that I mentioned, Dr. Ian Cunningham, who also developed an optical microscope, a low-cost optical frugal microscope to detect malaria. So now going to my question, have you tested your device, your malaria testing device into a clinical setting, like in humans? Have you tested your device, the malaria detection biosensor, in humans?
Well, yes, I have done a little bit of that work, some preliminary work. By the way, we had some collaborative study with the University of Cambridge, so I did some preliminary work on that. But then one of my, two actually of my master students are the ones that are trying to actualize that study. So what we have is the preliminary data. It's very promising, but then we need to do a lot of verification to ensure that actually what we are seeing is correct. But there is quite a number of studies that have been done on this. So our work is basically, or what we are proposing is to try and lower the cost of the device in terms of one, using cheap optics. And number two, one of the challenges, if you check from the published work, is that they have a challenge with getting a very uniform magnetic field. So we have a proposal that we are working on to try and see if we could be able to achieve some level of uniformity in the field of interest. Because if we can be able to do that, I think we could highly enhance the sensitivity of this type of device. The good thing about it is that since hemoglobin can also be used as a biomarker and it has a linear relationship with the infection level, then if we can successfully be able to actually fabricate something, it would find quite some interesting, or the uptake would be really received well.
Yeah, so my last question would be, are you thinking about commercialization? So, and if yes, are you planning to take it by yourself, or are you planning to hand it to potential graduate student who will spin this off and develop into a commercial product?
Sorry, there is a lot of echoing, so I cannot. Yeah, maybe you can without a mic. Yes, the idea is once, if the experiment are good enough, we should be able to commercialize the product. And previously, some years ago, there was very little emphasis in our universities about forming these spin-off companies to commercialize that. But now, in the last few years, there is a lot of emphasis on that. So we are hoping by the time we are doing this, we can be able to leverage on that goodwill to try and see if, because my idea is to form a spin-off company and then try and push the idea from outside. I think it's easier that way. Yes.
Hi, Dixon. There is an online question, and it is like, what's the sensitivity of the biosensors relative to the environment they are used?
What is that?
Sensitivity of the biosensors relative to the environment they are using.
Relative to?
Environment.
Or the environment they are
Yes.
used. Yeah, the environment is very, very important because, for example, the calorimetric biosensors rely on the fact that you are changing the refractive index. So if the environment changes, the refractive index changes, and therefore, of course, it has a direct influence on the outcome or the measurements that you make.
Then there is another question like, what's the projection of the strength of the magnetic field needed?
What is?
Projection of the strength of magnetic field needed. How strong magnetic field you need?
Oh, how strong the magnetic field, I believe, will be enough for this? Or in terms of Teslas, So for this experiment, the preliminary results showed that probably we might require close to 1 Tesla. Yes. But I don't know how we eventually, when we continue with the idea, what we end up with, because the previous studies that I've done, the guys who basically want to directly quantify this without necessarily minding about the uniformity of the magnetic field, they are able to use quite a very small intensity of the magnetic field.
Okay, with this,
Thank you, Dixon, for this very timely presentation. Just from the energy physics, just speaking from that question of the magnetic field, I don't know whether you have also factored the effect of the geomagnetic field, because I see you are trying to generate the uniform magnetic field. So maybe you can just comment on the effect of the geomagnetic field. Then my question now is, I see you are using the mixed research methods whereby you are having the qualitative and the quantitative. So maybe you mentioned that you used a COVID case that was, I think, 4 years or so. So how did you normalize your quantitative data, maybe for comparison purposes, with the qualitative? And which benchmark are you actually using? Thank you.
So thank you. I don't know about the first question. I think I've not thought about it. It's something that probably I'll have to think about after this. In terms of the second question, it's possible that, well, the whole idea is eventually we want to develop a device. And what that means is that if we really have to say this is the level of infection of a certain, maybe for example, COVID, then we have to have standardized methods. And one of those standardized methods is PCR. So when we take the measurements, the first measurement is done by PCR of the same sample, so that we are able to verify that or correlate the optical signal we are getting with the standard measurement.
With this, we would like to close this session. So let's thank the speaker again. Thank you. Okay, so because today we have a lab session, so after the lunch, we will be going to computer lab, the same lab where we were that day. Okay, thank you. So we will be starting in lab at 2 p.m. sharp.
Just a small communication as we go for lunch. We have issued all the participants and all the guests with the meal cards. They kindly have them as you show the waiter at the hotel. Thank you.